I've basically made a Z-pinch here.
Oh!
I got goosebumps.
Okay. It's time for some more Styropyro. Specifically 400 car batteries wired together. All right, and there he is. Glad he's doing well. For those of you who don't know me, I'm Tyler Fultz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
Hey guys, it's Drake Anthony here, and today I am bringing you some of the most extreme science experiments ever done on YouTube. Behind me, I have 400 car batteries wired together. With these batteries, I can pull electrical currents far beyond the typical lightning strike, and for much longer durations too. I can guarantee you that this video will be unlike anything you've ever seen in your life.
To be fair, I've seen the 100 car batteries, so 400, yeah.
You may have watched the video I did with just 100 car batteries. I did manage to pull some big currents there, but honestly, I did not utilize the full potential of those batteries. That being
Good electrical pun with the word potential.
said, the data I obtained from those experiments has prepared me to get the most out of my new ones.
All right, so we got strings of 5 in series and then parallel. So a typical 12-volt lead-acid car battery gives you about 600, maybe 1,000 cold cranking amps with internal resistance in the order of milliohms and peak short circuit currents in the thousands of amps. So all that times 400. So that'll figure out to 60, 65 volts for a string of 5 in series. So low voltage, ridiculous current, and a whole lot of stored chemical energy here. Yeah, we use a lot of battery strings in nuclear power plants for uninterruptible power supplies for a lot of our critical instrumentation and control systems, but never this many and like this.
So in short, even though I have 4 times as many batteries as last time, I'm actually expecting this bank to be 10 times stronger.
Okay.
Now the other thing about the first video is that it made the YouTube overlords a bit uneasy. Now don't bring out the pitchforks, that's all since been resolved, but in the interest of avoiding issues with this video, I feel like I should spend a bit more time covering the scope and safety of this video. So let me be clear that this is not a stunt. The purpose of this video is to explore the physics of extreme currents.
Okay.
I'm talking scales like you'd find in a national lab, but since this is all in my backyard, I get to have a bit more fun with it.
He's not at all wrong when talking about that. So, is the amperage going to be something like 150,000 sustained? You're getting into pulse power laboratories, touching on fusion Z-pinch experiments, and railgun power supplies is the order of magnitude that we're talking about here. The small difference is these national labs spend millions on switching systems and precision diagnostics, whereas just judging by the looks of it, he probably didn't, which is fine. But in terms of order of magnitude current, he is absolutely right.
And to be honest, much of this is just going to be me sticking random stuff in between the contacts to see what happens. And yes, I know this is a bit of a chaotic approach, but you know, this is really how a lot of scientific discovery happens. I mean, you know, the scientific method is great and all, but oftentimes, innovation is a product of just throwing things at the wall to see what sticks. So, why car batteries then? Well, as it turns out, car batteries are actually a great way of getting into electrical territory, where footage doesn't exist. When it comes to making huge currents, most people think of using capacitors.
Okay, that was pretty funny.
But interestingly, car batteries don't fall that far behind in terms of max currents. The benefit with car batteries is that they can
Trying to show what if it was a reversible process here.
dump those currents for far longer than a brief pulse. That means that with a bank of, say, 400 car batteries, not only can I produce the most current ever shown on YouTube, but I can do it for many thousands of times longer than the next contender. And let me tell you, there are so many interesting and important aspects of physics that show up at this scale. And I truly believe that all of this is going to offer an unprecedented look into the nature of extreme currents. So much so that I really think it's going to change the way that you look at electricity. So yeah, that is the purpose of this video.
I love it. What is this pose?
Now for a brief word on safety. I mean, it feels a bit silly for me to say don't try this at home considering, the sheer magnitude of this project. I mean, even a single car battery can mess you up if you screw up hard enough. So yeah, you definitely shouldn't wire together 28,000...
Anything could if you try hard enough, which is why safety is something that requires constant vigilance. And that's actually the real lesson here. This is on a much smaller scale, what he's doing is on a much larger scale than what most people would realistically try. And that is one common trap that you see that people who work in heavy industry where they deal with, tens of thousands of amps or volts or PSI or some other high source of energy and incorporate all of these electrical safety and personal safety procedures into how they do business at work. But then when you come home and you step things down to 110 volts AC and you let your guard down, don't do that, please. So I really appreciate this message here.
1,000 pounds of lead acid batteries in your yard, at least if you're not familiar with this sort of thing. But seriously, I think it's my safety that concerns people the most. And yeah, what I do on my channel can come off as pretty ridiculous and sketchy at times. But I will say this. I've been posting my mad science creations to YouTube since 2006. And let me tell you, it takes more than luck to do this kind of thing for 20 years without getting hurt. And that is because I am not a risk taker. And I realize that this must come off as the most ironic thing that I've ever said. But
he would have to not be in terms of doing something that is beyond, one, his capabilities, and two, beyond the postulated safety envelopes.
I never approach anything potentially dangerous without, fully understanding and mitigating the risks at hand. And no, I'm not in some fancy lab constrained by OSHA. I'm just a guy in my backyard with 400 car batteries. But I've dedicated my whole life to mastering extreme science, and I've slowly and carefully worked my way to the level that I'm dealing with today. So be assured, I know what I'm working with here. So now that that's out of the way, I want to briefly cover the issues I had with the 100 battery bank before showing the changes I made with this new one.
Oh.
I started by wiring them all in parallel, but due to contact resistance of the connections, I was limited to only 15,000 amps this way. I then rewired the bank for parallel strings of 5 in series, and the higher voltage allowed me to achieve a peak current of about 48,000 amps. In hindsight, I could have probably gotten more current from parallel strings of just 3 or 4 in series, but with this new bank of 400, I calculated that 5 in series, giving 65 volts, is what will give me the most current. So this is the
Yeah, it's about what I figured just by looking at seeing how it was arranged.
Number I settled on. Assembling the new bank took about 2 months, and manually placing all 14 tons of batteries was the easy part. Most of my time was spent digging in the plastic platforms, cutting and crimping 500 cables, and cleaning all 2,000 contact points immediately before joining them. And this is where the real challenge begins. How do you switch 400 car batteries? I've already mentioned that the kinds of currents I plan on dealing with are in a territory where footage doesn't exist, over 100,000 amps sustained. This also means that the kind of switch I need is in an uncharted territory as well. I need something that can slam the full power of the batteries to the loads as fast as possible, while also having the ability to disconnect power if necessary. Well, this kind of thing doesn't exist for less than the cost of the batteries, which means I have to come up with something myself. For the 100 battery video, I used a modified log splitter as the switch, and this worked pretty much flawlessly. Since it miraculously still works after sitting in my yard for 2 years.
Yeah, switches for these labs that require tens or hundreds of thousands of amps, the switches themselves cost on the order of millions of dollars, which is more than the cost of 400 car battery.
I figured I should just beef this thing up with a bunch more copper and steel. Now, since I need so much copper for the switch, I stopped by an unattended construction site and picked up a bunch of copper. So hopefully this will be enough to at least, get the switch wired. And then of course I might have to make a few more trips to wire the batteries. Now, as far as I know, this switch is going to be the biggest switch ever made for a YouTube video, at least by current. And let me tell you, when you're dealing with that kind of current, you run into some really weird issues. I'm expecting the switch to vaporize a lot of copper in operation, so that's why I'll be using the biggest blocks as the switch contacts. Now, I've saved machining them for last because, honestly, it's not that often that I get to play with pieces of copper this big. And actually, both of these blocks combined actually weigh more than I do, so yeah, there's a lot of copper here.
Yeah, Yeah, copper's a lot denser than a lot of people think.
Ugh, I just want to eat them. So what's something interesting that you can do with 2 giant pieces of copper? Well, let's try tossing a magnet down there. No, I'm not slowing down this footage. It's really just, moving through there at a snail's pace.
Oh, that's awesome.
Pretty weird, right? There it goes. I don't even need to drop it between the
I love how happy he is. I'm glad he enjoys doing what he does.
plates either. Like, just bringing this magnet close without even touching it, it's almost enough to knock over this 65-pound plate. If I go ahead and force it all the way to the plate, it doesn't want to just fall off. It's really slow down there. It's like it's moving through syrup or something. Yeah, it's a really neat effect. Oh, heck. Forgot that table's magnetic. So what causes these effects? Even though copper is not ferromagnetic, it is conductive, so it can still exert magnetic forces. Moving a magnet nearby induces currents in the copper, and it's these currents that pull on the magnet to slow it down. Silver is even more conductive, so these effects are even more pronounced in silver bars. There's a reason I am showing you these demos. Generally speaking, this intrinsic connection between electricity and magnetism has profound implications about how the universe works. More specifically, it foreshadows what's to come with the batteries. The currents I'm expecting will produce incredibly strong magnetic forces. This will make for experiments that look nothing short of witchcraft. That is, assuming I can even tame them in the first place. When I started tearing down the switch to make my upgrades, I noticed that steel shavings were sticking to it like a magnet.
Oh, yeah.
So I decided to investigate. So I got this compass here, and if I put it next to this this steel stock, it's a little affected, but it's not like, super strongly. But if I come over here, and I get just in the vicinity of this old switch here, you can see that the steel on there was very heavily magnetized by being close to such extreme currents. It's really nifty. This led me to a less nifty realization. The original contacts mysteriously wore on one side only. I assumed it was because of misalignment, although weirdly, the contacts look straight when fired with no load. I didn't think too much about it when it happened, because the switch still performed well. I realized too late that this was a magnetic issue. In the previous video, I showed you that currents going in the same direction attract each other, while opposite currents repel. What happened with the switch is that the opposing currents were magnetically repelling each other. The one side burned through was due to asymmetry in the cable arrangement. The daunting thing is that these forces scale with the square of current. That means that if I triple the current compared to last time, the magnetic forces will be 9 times stronger.
So, in nuclear power plants, we talk a lot about arc flash hazard, which is governed by current, fault energy, and how long it takes to clear it. Which is why switching is the real engineering problem here, just like you said. So 65 volts with upwards of 100,000 amps, yeah, that's going to create a lot of arc energy. And him talking about the scaling quadratically, doubling the current increases by a factor of 4, or like you said, tripling it increases by a factor of 9. That's the same problem you deal with in reactor bus ducts. Large generators feeding into switch yards can experience bus bar deformation during faults for exactly this reason. I mean, if that's part of the experiment is to create a bunch of arcing type events with this ultra high current, then yes, he is creating these sorts of failure modes. That's why utility substations have reinforced bus structures. So this guy is creating substation fault physics in his yard. All right.
This could cause some real issues. I still went ahead with building the new switch, and did my best to keep opposing currents as short and as far from each other as possible. I knew the magnetics could still be a problem, but since the closing spring is so strong, I figured it might simply just work as is. And if not, well, I can cross that bridge when I get to it. The finished setup looks straight out of sci-fi. Over 1,000 pounds of copper interconnect 28,000 pounds of lead. The work blocks are fed with 2 opposing loops of cable, which is in contrast to the single loop I used last time. This will cancel out the lateral magnetic forces that I had so much trouble fighting in the first video. I decided to start small with the initial experiments, mostly to rule out major issues before the currents become terrifying. For the first trial, I zapped a 3/8-inch galvanized steel rod.
Alright, here we go.
The effect was pretty much the same as when I zapped one with 100 car batteries.
That's good. He's starting out with the more simple tests to see what happens when you scale things up. I appreciate it. That's good engineering intuition.
Oh yeah, so you can see it left a nice little splatter there. Even blew off one of the threads, which is really strange.
Oh yeah.
I did more trials with these small rods to dial in my camera settings. Although these don't look very impressive at normal speed, the slow-mo camera I have set up tells a very different story. The fact that this rod is galvanized is a critical detail here, since the boiling point of zinc is lower than the melting point of iron. This means that the zinc plating boils off first, which reacts with the air to form this striking green plasma. When the
Aurora Borealis.
iron finally melts, it gets magnetically ejected upwards, which is not something I expected to happen. For the next trial, I zapped a small aluminum bar. Alright, pulled about 46,000 amps with that one.
Okay.
Nothing to write home about, but like a pretty strong lightning strike.
Talks about 46,000 amps.
The slow-mo turned out to be way overexposed, which is funny because it's usually a lack of light that's the challenge when filming at high speed. I ended up doing a few more trials in an attempt to get a better shot of the action. Look at that. It got pushed up and then re-solidified in that hilarious configuration there. That was definitely a magnetic force that pushed it upwards like that. It was difficult to get the exposure right with aluminum, since it burns so incredibly bright. But at least I was able to make out some of the finer details of the plasma fireballs in this one. I zapped a similarly sized titanium bar for the next trial. Kinda lame. I did find the slow-mo in this one to be pretty funny, since a random washer got sucked in magnetically, and a piece of titanium was spun violently as it was launched out.
That's great spin.
I stuck a small tungsten welding electrode on the blocks, and the current it drew was so low that it didn't even trigger my scope. The peak was probably a few thousand amps or so. Its white-hot incandescence looked super neat through the smoke of it oxidizing in air. At this point, I was ready to increase the current, so I started zapping some big bolts, with the first one being a 1/2 inch in diameter.
Well, that didn't last very long.
I pulled a peak current of 54,000 amps there, which is higher than anything I pulled in the last video, but it's still far from what I wanted, so I moved on to 3/4 inch bolts.
Oh man. Rain of sparks.
I could hear some sort of oscillation in that shot, which was picked up on my oscilloscope as well. The slow-mo showed some sort of bouncing around on the contact blocks, but it wasn't clear what was causing this.
I'm just saying, at any sort of, this isn't even just unique to the nuclear industry. Any industry that you get the NFPA 70E cert on electrical safety, there's a reason why it actually stands for National Fire Protection Association. Because, I mean, well, just take a look. And you look at these sort of events that are happening in like test breakers where you have essentially crash test dummies in PPE, test these out, and you're seeing the effects of the arc on the mock personnel, if you will, in the breaker room. So you're seeing this right here in someone's yard rather than in a breaker lab. To me, that is just wild. And again, I know he knows what he's doing, but it's just fascinating to see something like this.
When I did another trial in daylight, I could see that the oscillation might be originating in the switch. Jeez. Wow. Look at that. I think we had a full burn through there. In order to find the source of these oscillations, I zapped a bunch of copper cables of varying diameters as the loads. I suspected that the switch was to blame, so I pointed my slow-mo camera at the switch for the first trials. Going from 2-gauge cable all the way up to 4/0, I never saw issues with the switch. There were sparks from the initial turn-on, but the plate stayed closed.
Beautiful
Smoke rings.
Next, I repeated the trials of increasing cable sizes, but with the slow-mo camera pointed at the blocks this time. What I found was super surprising. It sounded like the cables were exploding, but most of them weren't even burning through. They were being magnetically ripped out of the clamps. This force came as a surprise to me, since I chose a wiring arrangement that cancels out lateral magnetic forces on the loads. Clearly, whatever mysterious upward force remained turned out to be incredibly strong.
So he's talking about the Lorentz force here. And the force between conductors is proportional to current squared divided by distance. So at the type of amperage he is drawing here in this setup, it's not merely a strong force. It is a violent structural force. When you get to high current densities, bus bars can literally bow. And this is why in nuclear power plants, seismic and fault analysis is required for every safety-related electrical systems, because some of them are high voltage and high current for a lot of big emergency core cooling system pumps, for instance.
When I made it to 4/0 cable, which as a reminder is the biggest American wire gauge size, this effect was quite dramatic. It was violently bent upwards. It managed to suck in all of the ferromagnetic materials nearby. It too did not actually burn through and instead was ejected from the blocks. In this shot, I measured a peak of 76,000 amps. The real-time view of this shot showcases some of the pros and cons of the low-voltage arrangement of the bank. It cannot shock me, which is nice. However, it also means it can't strike an arc across more than the tiniest of gaps, which leads to situations where the load is teetering off the block, ready to go off again at any moment. I have multiple ways to safely deal with these scenarios, but the science machete is my favorite.
Where's my science machete?
Oh, heck.
Thought I should point out that I'm not aware of any electrical safety related personnel protective equipment that involves the use of a science machete. Please let me know if you have.
Not enough?
That clang sounded like he was sword fighting with it.
Yeah.
You know what? I think he surprised me with that one. You would think after enough of these Styropyro videos I've seen, I would know what to expect, but I was not predicting science machete.
Yep, it's blown through. Yeah, it's fine. I should point out that my arc flash suit is more than adequate against these little sparks, and the magnetics make it impossible for me to fully short the bank this way. Now that it's daylight, you can see that the 76 kiloamp shot just completely welded that cable to the plate there. It's just well, okay, it came off, but it was yeah, that was really stuck on there. At this point, it was clear that the block mounts were an issue, but that didn't mean that the switch wasn't an issue as well. So I decided to sidestep the block issue by C-clamping the copper cable loads. Now I need to bring up why I've been using spring clamps instead of C-clamps. If you watched the last video, you saw that when I zapped bolts, I had a lot of trouble holding them on the blocks. The fact that I was using spring clamps to hold them down, and not C-clamps, infuriated a lot of viewers. So many people commented about this, many of them calling me names for not using C-clamps, vices, or some other threaded mechanism. It's my fault for not explaining this the first time. And I get it, C-clamps are so much stronger, right? Well, the fact of the matter is that you cannot use C-clamps to hold a round, rigid object on the blocks. C-clamping a bolt onto the blocks will always lead to the bolt being ejected before it melts. It does not matter how hard you tighten them, this will happen every single time. There are a few reasons for this. For one, the outer surface has an oxide layer, which means that the contact regions have lower conductivity, and thus heat faster than the bulk metal. Plus, in the case of round objects, the current has to pass through a small area as it jumps from the blocks, which also dramatically increases the heating near the contact points.
Sure, yeah.
To make matters worse, hot metal is more resistive than cold metal, meaning more energy is dumped into the hot areas, leading to thermal runaway. All of this results in the contacts quickly exploding off, shrinking the contacts to the point where they're no longer held by the clamps. Spring clamps, however, follow through with the shrinking load, holding contact with the block until the load finally melts. Of course, this is unless the magnetic forces are stronger than the clamps. That being said, C-clamps are still useful with flat objects, or loads that can be spread flat like stranded cable. The reason is that this moves the part of the load that melts to outside the grip of the clamps. Thus, for these next trials, I C-clamped stranded cable to the blocks, in order to see how the switch would behave with a well-secured load. The first test with zero-gauge cable gave an interesting result. It looked and sounded like a perfect shot. Something to note is how fast the sparks shoot out from the exploding cable.
Yeah.
The slow-mo shows that the cable did indeed burn through, and judging by the spacing between the blocks, the cable end was thrown back at a speed of at least 190 miles per hour. However, the scope shows that this was actually a bad shot, since it was split into two pulses of about 76,000 amps. Since the load was well secured, this implies that the switch bounced. Zapping two zero-gauge cables in parallel gave unmistakable proof that the switch was indeed bouncing. As violent as this looks in real time, the slow-mo is far scarier. The switch managed to launch a toroidal plasma vortex into mid-air before blowing open. Honestly, I think I'm better off not knowing what kind of temperatures are involved.
When you hear toroidal plasma, when I hear toroidal plasma, I just think of tokamak fusion reactor, not something that is launched via C-clamps and 400 car batteries.
Allow an ionized copper plasma ring to exist in air. Regardless, it's obvious that the plates are getting completely blown apart here, which is most likely a magnetic issue. For the sake of data, I zapped even thicker cables, and the switch plates continued to get blown apart. The C-clamp struggled to hold down the cable in a couple trials as well. The scope showed that I was reaching peak currents of nearly 90,000 amps, and although this is triple the current of a typical lightning strike, it's still far less than what I had hoped for.
If he's talking current, sure. Lightning peak current is typically on the order of 30,000 amps, and at the extreme end, maybe 200,000. So he's in that ballpark, but the difference is lightning has millions of volts, he has 65. And the plasma associated with lightning, that channel's on the order of kilometers. I know he knows this, but strictly talking current, not talking total energy here with respect to lightning.
Clearly, I need to find a way to keep the switch closed. The fact that there are opposing currents on opposite sides of the switch means that there are tremendous magnetic forces that push the plates apart. Some napkin math implies that these forces are on the order of a ton or more. This is on top of whatever...
That's definitely plausible, and that is what causes bus bars to bow. A ton of force, literally.
Explosive forces exist from the superheated plasma that forms in the switch. How can I combat this? The first idea that came to mind was to slap some huge springs on there, because at some point a brute force tactic like that has got to work. But something about that just didn't feel right, though. And then it hit me. I shouldn't be fighting the magnetic forces. No, I should be working with them. I realized that the switch plates would attract each other if I could manage to get light currents going along both plates.
Sure.
The easiest way to do this, at least using what I had built already, seemed to be by rearranging the switch cables from an X-shaped configuration to a Z-shaped one. That way, there would be a component of current going along the length of the plates, which would magnetically bring them together. After thinking about potential issues of this arrangement for a while, I decided to just try it out and see what happens. Rewiring the switch took me 4 entire days, since I had to re-clean every contact point that I had exposed. An unfortunate reality of this project is that any changes to the circuit are very time-consuming. The initial tests with smaller loads like steel rods and aluminum bar were promising, so after these, I went back to zapping 4/0 cable. The first cable behaved in a strange way. Both C-clamps were completely ripped off the blocks, and the cable basically exploded without melting. I clocked a peak of 94,000 amps, which was only a slight improvement from before. I used 4 C-clamps for the next shot, but the cable was still ripped out of the clamps before fully melting. The third shot finally gave a complete burn-through. However, the switch was still bouncing. It sounded much more violent than before, and the pulses were spaced closer together, but the current hadn't gone up by that much. I hadn't even hit 100,000 amps. When I did more testing...
Oh darn, I haven't hit 100,000 amps. I love hearing his process.
The next day, I struggled to hold the cables on the blocks and made these silly oscillators as a result. The mysterious magnetic ejection force had become much stronger after rewiring the switch. After adding more C-clamps, I eventually got to the point where I could melt a cable again. The slow-mo of the switch showed more toroidal plasma vortices and even angrier explosions. What was blowing open the switch now? The answer finally made itself clear. Okay, so you can see the melted wire there, which is interesting, but the real interesting thing is this. So here's the blown up, switch plates, and can you see that hole there? So it's on both sides. I've basically made a Z-pinch here.
Oh!
I got goosebumps.
Okay. That's fascinating. So that occurs when current flows through plasma and the magnetic field compresses it inward. And this is a real fusion confinement concept used in pulsed fusion research such as Sandia National Labs' Z-machine.
When I first saw those craters, because I realized I had encountered a phenomenon of astronomical proportions. The switch was triggering a magnetic implosion via a Z-pinch. This is such an extreme phenomenon that it makes every project I've worked on up to this point seem like a joke by comparison. A Z-pinch is the effect where a current conducting plasma is crushed inward by its own magnetic field.
Yep.
Some less extreme examples of the Z-pinch occur in lightning and electric arcs, and it's what holds the plasma in a thin filament. My best guess for the sequence of events in the switch goes like this. When the plates first come together, the high points explode off and ignite a plasma, perhaps causing an initial bounce. The huge magnetic field then causes the plasma to implode into a thin filament. This leads to millions of watts of power being dumped into a tiny volume, yielding temperatures beyond my comprehension. A Z-pinch is balanced when the magnetic pressure inward is equal to the hot plasma pressure outward. At 100,000 amps, these pressures are so extreme that they can nearly induce DT nuclear fusion.
Not quite. Fusion's going to require over 100 million Kelvin temperature and much higher density confinement than that. And the plasma has to be stable. So what he's producing is just still very impressive in this Z-pinch. Not sure if that was intentional or not. is localized copper plasma with very high temperature for microseconds. Fusion devices are typically going to operate at millions of amps. He's maybe 100K. But even if he had that much current, it requires precisely shaped pulses and a controlled geometry. This is wildly impressive, but no, it isn't fusion grade. Thankfully. I don't know if he intended to prep his yard for a high neutron dose. Because deuterium-tritium fusion reactions still makes neutrons. Even though neutrons are not what cause fusion, they're going to be a product. But the fact that he saw those craters from magnetic collapse, yeah, that's Z-pinch. Focused plasma chaos in your switch. Again, I don't know if he did that on purpose.
The thing is, though, a Z-pinch does not form a stable plasma. I can only speculate which mechanism destabilizes the plasma in my switch, but whatever it is, it goes off like a bomb. I figured I had to either vent the plasma gases or disrupt their formation early in order to get the switch to close. The first thing that came to mind was to add some copper cable to the plates. This didn't exactly work and managed to spray liquid copper everywhere, but I felt like I was onto something. I added much thicker copper cables along the switch plate for the next test. What the heck? It was so violent. Whatever happened there was significant. The bolts holding the copper blocks were ripped through the wooden mount, and the cable was magnetically crushed into a smaller diameter. I have to go take a look at the current. I think we had another 94 kiloamp shot there. Kind of odd how flat top it is.
Interesting.
You know, that's interesting. I might be getting far higher currents than I expected. Because the fuse current equation, that is very much in line with a 150 kiloamp
Okay.
shot.
So over 100K. Still not in fusion territory. I'm not sure what his goal is, if it was 150 or not.
Interesting. At this point, I realized the numbers were not checking out. Now I should bring up how I'm measuring current here. In the first video, I just looked at the voltage drop across the cables, which isn't very accurate and only gives meaningful results when the current hits a steady state. For this video, I bought the biggest Hall effect sensor I could find that listed a price, which is this one rated for 20,000 amps. I've been feeding the cables from one of the 8 sub-banks through it, and then
Yeah, he's absolutely going to saturate that.
multiplying the value by 8 to get total current. However, this seems to be measuring far too low based on how fast this cable melted. I had previously made this spreadsheet to predict how fast cables would explode at a given current, and it's based on the Onderdonk fuse
Experimental
equation.
data.
It predicts that 150,000 amps are necessary to pop a 4
I like the vomit on the unit of area in circular mills. Yeah, every now and then you run into some really cursed units when you do this sort of stuff.
cable in 70 milliseconds. I suspected that the sensor was saturating, so I removed 4 of the 5 cables going through it, and then added a factor of 5 to the scope readings. I struggled to get a nice clean pulse in the subsequent shots, but I eventually achieved one good enough to confirm that this fixed the sensor issue, and I was indeed achieving far higher currents.
Nice.
That was 138,000 amps.
Okay, so he's been getting a high current earlier. Well, that's great. I'm glad he discovered that. Just a classic instrumentation error. In nuclear engineering, you never trust a single instrument reading. That's why a lot of things, like, say, reactor coolant system temperature, for instance, a lot of them have redundant sensors, some of them that are right next to each other, and some of them that are a little bit further away, just so you can do a quick reality check. But there's a whole bunch of instruments there. A lot of them, the reading is powered from safety-related buses, low-voltage buses, that are backed up by UPSs with battery strings that look like this. Well, maybe not like this, but it does involve battery strings, so it's kind of funny how it all goes back to that. But yeah, I appreciate him reverse engineering current calculations from thermal destruction rates, because he has all this experimental data here that he can use to kind of backsolve. That's a very interesting way to do it, but that is exactly how some accident modeling scenarios validate this sort of thing. And a lot of scenarios do what's called bounding calculations, which means if your numbers won't exceed this known number that is known to be the minimum that causes a catastrophic failure, and you're going to apply some conservatism, so you're going to lower that threshold to say, okay, what your real safety zone is. So you'd have like your actual failure, your design limit, and then you have your operational limit for, it can be anything. It could be on current, it could be on reactor coolant system pressure, temperature. But the point is, you have these bounding calculations that if all of your parameters for a given scenario do not exceed a certain number, then this scenario is indeed bounded and vetted, if you will, by the current design basis accident model, which is usually pretty extreme in the case of nuclear power plants, which is why the safety systems are so robust to protect you from not just the most realistic accident, but the most realistic accident with an extra multiplication factor applied on top of it, so you're absolutely sure your systems are safe. There's an old joke that for nuclear engineers, 2 + 2 = 4, but let's call it 100 just so we're absolutely sure that we're good.
I am just in awe. And it can go higher. There's more.
Now, how about that? Like, you underestimated how much current you were drawing, so you were actually doing better than you thought you were. I mean, in this case, if his goal is to draw a lot of amps, but he knows he can do more. I love it.
138,000 amps. This is big progress. Big progress. Wow. I need to go eat and Just the obsession, man. What a project this has been. Kept adding more cables to the plates, but I never got another clean shot this way. So, for the next configuration, I stuck one of the original switch plates in between the new ones. I was hoping it would weld itself on there at a slight angle to vent the plasma. So, the C-clamps actually failed on that shot, but I did pull about 110,000 amps, and the plate, somewhat welded on there. It's funny how, poor of a weld will still conduct really well, and that's just because the contact points will melt, and then there's very, very little contact resistance when that happens. So yeah, let's blow up another cable. This wasn't working, but I suspected that if I allowed the zaps to go on longer, it might just finally close. So, I stuck two 4-aught cables on the blocks, which quadruples the amount of energy dumped in the shot compared to a single cable. This led to the most violent display of electromagnetism I've ever seen in my life.
Wow.
Liquid copper was shot above the treetop level here. I measured a peak current of 140,000 amps,
Wow.
which gives a total circuit power of 9 megawatts. Yeah, look how...
Yeah, simple equation, really. Power equals current times voltage, and the voltage is stable at 65. That's small power plant territory for that very infinitesimal period of time. So, yeah, microreactor scale power from an energy flow standpoint. That's... That wire piece got blasted back there while it was still borderline molten, and it just wrapped around that handle there. It's incredible. Actually exploded on both sides. Over here we got copper just painting everything. Even the ground is now copper plated. Just all the boiling copper getting sprayed everywhere. It's unbelievable. I was about to attempt a new switch configuration, but then I realized that was actually really awesome. Maybe I should try jamming some weird metals inside the switch itself, at least before I attempt to fix the real problem here. So on this one, I'm going to try to weld this copper plate onto the big plate here, and I also have a piece of steel in there. So hopefully it makes a lot of sparks. Is that enough?
The current didn't get particularly crazy here, but it still made a very nice shower of sparks. There's not much left of that steel plate there. It's really welded on there. Yeah, that plate is a little hotter than I realized. Yep, quite toasty. I stuck a puck of zinc in the switch for the next shot.
Oh.
Unfortunately, it was ejected from the switch nearly immediately. Other than the initial explosion, the sparks here are just from the copper switch plates hitting each other. I'm thinking that maybe aluminum would, is the solution here. Let's try putting this in the switch. Holy! What the? What just happened? What on earth just happened? That was so violent. Wow. That was bonkers. That was so violent. The copper cables were completely launched. Oh, interesting. It ejected, how did the ingot end up out here? What? I have no idea how that happened. That iron bar there got pulled off the ground magnetically. I'm just trying to notice all the details on what actually happened here, but that's ridiculous that the ingot was ejected. I had placed a bunch of bolts on this little table before that shot in order to see how they would be affected by the magnetic field. A
Aluminum works well for illuminating slow-mo shots since it burns so brightly in air. As you can see, the bolts were quickly sucked in by the magnetic field around the cables. It's funny because I've lost a lot of tools this way, and that I've left them too close to the cables before firing the bank. A detail I'd like to point out is how the steel post and winch redirect some of the magnetic fields, and that's why a few bolts get trapped in their vicinity. The aluminum was violent enough that I did a few more trials with it. In this one, a smoke ring was shot out sideways from the smoke plume. I have no idea how that's even possible.
Wow, sideways. I guess when it was just jostled around and it happened to be at that precise angle.
In this,
When you're dealing with numbers that big in this sort of environment, this open environment, yeah. Any little field perturbation here can cause weird things to happen.
shot, it's the sound that stuck out to me the most. I've noticed that so many of the sounds I've heard from this project are unlike anything I've ever heard before. These batteries are capable of some truly unique audio effects.
So this is that aluminum block that didn't quite all the way melt inside the switch contacts. It got close, but not all the way. So I'm going to put it on the yeet blocks this time.
Even though I had yet to solve the switch issue, I realized that the peak currents I was achieving might be enough to pull off the most important demo of this video, and that's magnetically crushing a pipe. So why is crushing a pipe the most important demo? Well, I tried this in the last video and failed miserably. Even when I let the pipes melt from the current, they were still not crushed by the Z-pinch effect. At the end of the experiments, I said this.
Since the pressure on the pipe is proportional to the square of the current going through it, that means I'm not even getting close to what's needed at 40 kiloamps. Now, if I had a few hundred more car batteries, well then yeah, I could pull it off. But for what that would cost, I'd rather build a more accurate lightning machine. Now I bring this up because this car battery series was not my idea. I was actually hired to make these videos by the company AnyDesk.
So what about the lightning machine?
No, they don't make car batteries. I'll tell you more about them in a bit. So what I'm getting at is that these maniacs bought me 300 more car batteries and another half ton of copper just to see me crush a pipe. So yeah, this one's pretty important.
Oh,
I want to quickly add that if you have ideas for ridiculous experiments that you'd like me or another YouTuber to try,
a request by a sponsor, that's fascinating.
Submit them at anydesk.com/science. It only hit me when I set up for the first pipe crush that this might be more difficult than I expected. Although these batteries are capable of pipe crushing currents, the circuit is slow to turn on. The combination of a bad switch, low circuit voltage, and cable inductance means that the pipe might melt before the current reaches crushing levels. A few attempts with various fuses did not manage to crush the pipe. Next, I decided to stick the unfused pipe on the contacts to see if it would at least crush while melting.
It blew off both sides. Oh, that's crazy. I don't even know where it went. Well, I did see something over here. It's crushed. It's crushed. There it is.
Wow.
It was crushed. Look at that.
Just like his equation predicted. Pressure being proportional to current squared, which current being proportional to magnetic field strength. Yeah, cranking up the current at north of 100,000 amps relative to 40, yeah, that's going to give you a lot more pressure.
Of course, it was brought to the melting point, so in some way it was kind of cheating, but still, this is like, you know, I could not do this with a 100 car battery, so I'm really happy to see this. It actually crushed the pipe.
So this is the same principle used in pulsed power metal shaping and plasma confinement. So he basically built an electromagnetic compression rig by wiring up 400 car battery. All right.
That's amazing. I'll have to take a look at the current. Just want a better shot of that waveform. It's really only like 90,000 at the peak.
Okay, 90,000. Fair enough. This is proportional to its squared. A little bit of current goes. a little bit of current change will have a much larger effect on how much force is provided using the magnetic force equation.
But, hey, it did it. It did it. So I actually managed to find the pipe that I tried, directly melting and crushing with my 100 car batteries. You can see how it didn't crush at all. So it's really cool to see that's what the increased current does. So
the difference between 100 and 400 car batteries.
They both melted on both sides, but clearly the 400 car batteries really made the more dramatic crush there.
I still wanted to crush a pipe without it melting though, which meant I had to go back to using fuses. When I tried zapping an annealed pipe, I lucked out with a perfect shot of the switch. However, it did not crush the pipe. I clearly needed more time for the current to rise, but using any bigger of a fuse would melt the pipe first. That is, unless maybe I could try water cooling it. I found this aquarium in the woods years ago, and since I haven't put any fish in it by now, I figured I might as well use it for this experiment.
All right.
I really hope that this works because I don't know what I'm gonna do if it doesn't. I mean, I put a lot of stock into the idea that I was gonna easily crush a pipe with these batteries. But yeah, it turned out to be harder than I expected. So yeah, I'm really crossing my fingers that
That's your sponsor for more car batteries.
this one works. So I'm gonna use this this giant flashlight here at full power to illuminate this, so my my slow motion camera can see it. And I'm gonna need a lot of light. Okay, here we go. Get ready to sprint. So
All right.
explodes, then I hit the button. Here we go.
This tree will surely protect me.
Okay, what happened?
The slow-mo shows that the magnetic forces broke the aquarium right off the get-go. Then the pipe started to crush, but then it exploded. Clearly, everything is happening way too fast here for the water to do anything. The ends of the pipe were crushed when it exploded, but this isn't much different from what happened with the unfused pipe in open air. Notably, the switch performed horribly in that shot, and this was a good reminder that I should go back to solving that glaring issue. Zapping smaller loads showed that the switch wouldn't bounce until the current rose to around 100,000 amps or so. Maybe all I need are some huge springs to hold the plates closed beyond that. This seemed worth trying, but I was too impatient and zapped a few more items before making modifications to the switch. I was particularly excited to pop these magnesium anode rods.
Here we go.
Wow.
What? It blew up my fuses.
It took the fuses with
As
it.
you can see, it blew up all those fuses.
Imagine that the safety-related current interrupter device broke on high current.
And the magnesium won.
The magnesium.
I see that they all melted
That I didn't
at
predict.
the like at the lugs there. It wasn't the wire that melted. It could be that the
Not a
fuse
lot.
current of those lugs is lower than the actual quadruple-aught cable.
When upgrading the cable fuses, I noticed that 2 of them had been untorqued from the magnetic forces, allowing some corrosion to get between the contacts. With bigger fuses and clean contacts, I was able to achieve even higher peak currents. I got a particularly impressive number when zapping the zinc plate. Due to fresh fuses and hot weather improving the battery performance, I achieved a peak current of 176,000 amps with this shot.
Now, something I wanted to point out is, so I tossed this makeshift just little wooden cover over this actuator that pulls out the pin that fires the switch. And as you can see, it's taken quite a beating. It's just coated in copper there. Now, the funny thing is that I had these copper wires that held it in place, and those melted before the wood gave way. Wood is like a surprisingly resilient material against plasma blast. It's the same way with lasers too. So it's funny how the wood outlasted the copper there.
At this point, I realized I had to quit procrastinating and decided to go ahead with welding some big springs to the switch.
Well, I will say one thing. These batteries, they don't scare me. What does scare me are these springs here. I have to load them up with the ATV winch. So, yeah, these are less predictable. I don't know what these want to do. My welds could rip off, bolts could snap, who knows. These batteries, I feel like I have a good idea of what they're capable of. Okay.
I don't know, as a nuclear engineer, seeing this setup, now, I don't have the skills that he does, be first to admit that, but yeah, both of those would make me a little nervous. Not sure which more. I mean, I get what he's saying with the springs, but 150, was it 170,000 amps that he's getting here? Yeah, a lot of shrapnel, a lot of explosive plasma expansion, can vaporize copper and a lot of material instantly. And this temperature can exceed 20,000 degrees Celsius for the arc itself. Again, we're not talking anywhere close to fusion conditions, but it's more of the arcing hazards is probably the primary hazards that are associated with it than if you could somehow get neutrons from this, that no. Just no. But yeah, a good thing is the voltage is low. I mean, if this was 400 in series, so that'd be 4800 volts-ish, that'd be a little different. Plus, the batteries are going to generate hydrogen gas, and there's a reason why in every battery room you have vents, so that you don't get a flammable concentration of hydrogen. Those vents exist in every battery room in the nuclear plant. The good news is he's outdoors. So well-ventilated area. But 30,000 pounds, however much all this weighs, of lead-acid battery bank, still not trivial amounts of hydrogen gas. And beyond that, just a lot of mechanical forces. Over a ton. That's why nuclear switchgear's fault-rated gear is massively braced. Bus bars are rigidly supported, and clearances are engineered. This is all very different, but ultimately, I get what he's saying, and I appreciate him discussing the safety, but yeah, to me, this is all kinds of craziness out here, which I love watching.
I've got these springs mounted on here. That way the internal spring, as well as these new springs, make a nice little triangle there. And I'm going to finally test it to see how it works. I really hope this keeps the switch closed. Scopes ready? All right, here we go.
No, your video player didn't lock up. I just wanted to take this moment to admire the incredible light output of these copper plasmas. Anyway,
I can't tell what happened. It seemed oscillatory, unfortunately.
Unfortunately, the switch was still bouncing. The new springs added so much tension that it maxed out the 1,600-pound hand winch I used to load them up.
Wow.
And yet they barely hindered the bouncing in the switch. Shorting one car battery may be easy, but shorting 400 takes a feat of engineering. I initially discounted the idea of using solid-state switching, but out of desperation I revisited the idea. Much to my surprise, I found that big SCRs were more than capable of switching the batteries. However, I couldn't find a single distributor that had big ones in stock, so I had to resort to brute force tactics. I bought another log splitter. I should point out that I've been using the hydraulic part of the log splitter to open the switch, not close it.
So switching systems at this scale in national labs use explosive openings, or vacuum spark gaps. So this is going to be interesting.
The idea is that the tough hydraulics can rip apart the plates when they weld, and it's functioned perfectly for this purpose. However, its big internal spring I've been using to close the switch is clearly not enough. Adding a second log splitter makes the closing action hydraulic as well, but it comes at the cost of moving much slower than the spring. In addition, I added some rails and reinforced the entire structure with a bunch of steel posts. The reasoning is that the slow-mo shots had shown the plate sliding sideways from magnetic forces, so I wanted to lock everything to one axis to prevent that. I had a little mishap when I tested the return springs I added.
Oh, shoot. That was what I was worried about. Oh, it just straight up sheared off the hook. See, that's what I mean when I say springs are actually scary. Electricity doesn't scare me. Springs scare me.
Yeah, I get it. The unpredictability here.
Ended up just foregoing the return spring since the internal one seemed adequate.
All right, for the first test with the two log splitters here, I'm going to zap 2 more of those quadruple aught cables just because they have a very predictable fusing properties. So yeah, I really, really hope that this works. All right, here we go.
More smoke ring.
That was good. That was very good. I liked that.
The scope showed that the
oscillation.
switch bounced at first, but it did eventually completely close when 160,000 amps were passing through it. The slow-mo confirms this as well, as the switch quits making sparks before the cables explode. The drop in current at the end was from the cables getting magnetically ripped from the blocks. Further testing gave the same results. The switch would initially bounce, but it would still close afterwards. I had to concede that this was gonna have to do. I needed to continue on to the main experiments before autumn temperatures got too cold and put too much of a hinder on the current I could pull from my batteries. It took me months, but now I finally reached the point where I can hold sustained currents of over 150,000 amps.
Wow. And to think he brute forced with hydraulics and copper what a lot of national labs spend millions on. That's quite clever.
You're about to see what this kind of current can do to small objects, but I still think it's worth giving you a sense of scale and just how incredible this number really is. So, how big is 150,000 amps? Well, this is fusion reactor levels of current.
Again, not quite.
And this is enough to ignite DT nuclear fusion in a Z-pinch fuser.
Okay, if he's talking, a fuser. So we're talking brief pulsed fusion, maybe some trace DT neutrons that you would measure if tritium happened to be present. But if you're talking actual Z-pinch fusion, you're a couple of orders of magnitude short. The Z machine at Sandia National Labs is on the order of 20 million amps. So fusion requires high temperature, high density or pressure, and high confinement time. Current gives you the high density, strong force, strong magnetic field. So 150,000 amps, assume plasma radius of millimeter. I'm being generous. You're going to get magnetic fields on the order of tens of Teslas, which is a lot. I mean, that's more than a MRI. But for serious Z-pinch fusion work, you're going to need on the order of hundreds of Teslas. And that's still not giving you hundreds of millions of Kelvin. And that's still not giving you your 100 million Kelvin and your sustained confinement time. The real killer here with sustained fusion is going to be the instabilities. So it's possible to cause a few microscopic, brief, individual fusion reactions that on a macroscopic scale don't really amount to anything, but nowhere near enough to achieve what's known as ignition in fusion. If 150,000 amps were enough, man, we would not need multi-billion-dollar national lab facilities or decades of plasma physics research. It'd be a lot easier to pull off. So I get what you're saying, and it's possible to have some localized pulse fusion events like the fusor he mentioned, but if you're talking actual fusion.
This level of current exceeds the entirety of the auroral Birkeland currents that surround the planet on a typical day. It also far exceeds even the top 1% of lightning strikes, and in fact, the charge transfer during a single shot from these batteries is more comparable to an entire thunderstorm's worth of lightning bolts. Now, I get to screw around with these baffling levels of current.
I would compare this more to plasma-focused devices, railgun power supplies, and, well, like you said, individual Z-pinches, but not a fusion ignition system. I mean, after all, if he did, he'd have to worry about neutron flux out here, where there's no shielding.
A 1-inch bolt was the finale of my 100 battery video, so I'm curious to see if it's much different with 400 batteries.
Wow, that was a lot of sparks. That was really cool. Wow. So in the previous video, I made a crowbar circuit. So of course, I want to try it with the 400 car batteries this time.
Of course.
Now, as a review, a crowbar circuit is a real thing. It just usually doesn't mean using a literal crowbar for it. It just means to have something short the power supply rails to protect the rest of the circuit. So yeah, let's see how long this thing will hold up to the car batteries.
All right. And here we go.
Literal crowbar circuit.
Whoa!
Everything's on fire! Oh, that's beautiful. Dude, that's insane. Look at all that hot metal. Look at all that hot metal.
Yeah.
It's like burning the dirt. Look at that. All that just it blew it up into a bunch of chunks. That's really crazy. It didn't do that last time.
My friend James brought over his dad's old wrench to see it zapped by the car batteries.
Where's the leak, ma'am?
Oh my.
Whoa, what? Wow.
Flaming wrench.
That broken like.
Yeah, it broke in a bunch of spots.
Just like what happened to the crowbar, the magnetic forces on the wrench broke it up into several pieces when it melted through. I still hadn't figured out where this upward force was coming from, but when I zapped brass bars, I had an epiphany. The big bar suffered the same fate as many of the cables I had blown up, in that it was magnetically ejected before it could burn through. It still made an impressive display of sparks, though. It was the small bar that gave me the revelation.
It got launched, didn't it?
The bar melted on both ends and was ejected perfectly upwards, being sent into a fast spin as it was launched. The bar solidified into this bent shape, which I figured approximated the equilibrium state of forces on the bar when it's on the blocks. I've already mentioned that the forces from the opposing loops of cable cancel out, which meant that the upward force must have been coming from the fields of the nearby path of current feeding the loads. I realized that an object off the axis of the main current would be exposed to much stronger fields than an object in line with the current. The fact that the current had to make the small bend off the blocks was the origin of this super strong force. The funny thing is that this explanation is actually wrong, but it still gives the right result. Mounting objects closer to the center of the block ends would reduce these forces. When I zapped a kilogram ingot of bismuth, I was able to jam it in the middle well enough to minimize these forces. This was one of the most impressive burn-throughs I achieved with the batteries, and there was very little left of the bar afterwards. The slow-mo shows that much of the metal likely boiled off, giving these incredible plasma fireballs, as the metal vapor reacted with the oxygen in the air. The yellow color of the smoke is due to the bismuth trioxide that was formed in the reaction. I zapped a big block of zinc, and although it wasn't particularly noteworthy, it did lead to something funny.
So look at this ridiculous thing. So these blocks were sitting on the ground and got magnetically sucked in there. Then they shorted and welded themselves together.
Zinc gives far more beautiful effects when it's plated onto steel, like on this galvanized pipe here. It's funny because I zapped all sorts of weird and exotic metals for this video, and humble old zinc stole the show from all but a few of them. Zinc's fairly high reactivity, paired with its unusually low boiling point, gives unique effects unlike any other metal I've zapped, other than maybe bismuth. The fact that zinc burns green at a modest light level is what really takes the cake when it comes to slow-mo filming,
Gotta have the green glowy stuff.
I zapped a couple titanium bars, and although they were cool, they were so bright that I failed to get good slow-mo footage of them. The most notable effect from this trial was that the two bars magnetically attracted each other and welded themselves together. I zapped some pieces of zirconium, which is among the hottest and brightest burning metals.
There we go.
Wow, that was bright.
That was so bright.
Much like titanium, zirconium was so bright that it too was challenging to capture on camera. It feels weird for me to complain about something being too bright, but the enormous contrast in light levels is difficult to squeeze within the dynamic range of even a nice camera. I substantially dialed back the exposure on the slow-mo shots compared to most other metals, and they still ended up on the overexposed side. Now that being said, I love how well the little popping pieces of burning zirconium show up in these scenes. I revisited titanium in the form of little chunks to make another attempt at slow-mo. I cranked back the exposure, but it still wasn't as much as I should have. Now that being said, it still showcased similar popping sparks to what I got with the zirconium. As a bonus, this shot made a perfect smoke ring as well.
Oh yeah, look at that.
I was curious how this configuration would work with a bunch of Abe Zinken pennies.
Is Abe
Pour
Zinken?
one out for the U.S. penny. Ha! This one I see I shot with a laser at some point. Funny.
I love Abe Zinken. Some purple in there? Yeah.
So there was one really, really big spike there. Like about 140,000 amps for a short bit. So that's... Wow, that was actually more than I expected, but of course it was very brief. That's hilarious.
I was surprised how violently the pennies were ejected from the center like this. But then again, weirder things have happened at 140,000 amps. Yet again, zinc showed off its beautiful pyrotechnic colors in this shot, which were likely complemented by the copper shells that surround the zinc cores.
Oh yeah, there it is.
The thick and delicious zinc oxide smoke seems to make filming the burning metals so much easier, as the smoke diffuses the light and limits such stark contrast in light levels. I tried the same configuration with a bunch of bolts and nuts to see if ferromagnetic effects would change anything.
Smaller.
Wow, look how much different that was. So they didn't even get ejected. They all just stayed there for the most part. I guess they were magnetically sucked in there. That's really interesting. Wow.
Self-stabilizing.
Yeah, look at that. Just one
Wow, a big
giant
chunk.
mass that all melted together. Now that is an abstract art piece there. Beautiful.
I revisited aluminum and had a few notable shots. In one trial, it made a really cool sounding oscillator.
Whoa.
The lens on my tree camera was hit in another shot as well.
Man, this is all crazy. Like you said, not a stunt. Pulsed power research in someone's backyard, right on the edge of where national labs take over.
Since aluminum burns so brightly in air, I wondered, would it burn in the same way if I zapped some underwater? When I tried crushing a copper pipe underwater, it ended up just exploding, but it made for really cool high-speed footage. I found another aquarium in the woods to attempt this setup with aluminum cable.
Alright, so camera, flashlight, yeet, camera. Flashlight. Okay, think I'm ready.
Behind the tree.
Glass went absolutely everywhere on that shot. I mean, everywhere. Water went everywhere. My cameras are soaked. That was ridiculous. That thing blew up so violently. Okay, I really hope that was good. Whoa! Oh my goodness. Oh, that was a cool shot. Wow. That was beautiful.
Glad he
Okay,
admires it.
yes. That's what I wanted.
Only the Lord decides how the switch will perform in a given shot, and this was its slowest turn on of the entire video. Now, this gradual ramp up of the current actually made for some interesting slow motion effects. Once the aluminum was heated well beyond the boiling point of water, the Leidenfrost effect became apparent through these neat oscillating bubbles. The switch managed to close about a millisecond before the cable melted, pushing the current to around 70,000 amps as it exploded.
Okay, that amperage is gonna kick aluminum up to boiling in microseconds. And I can see in that shot, looked like the surface oxide layer came off. Plasma forms, and it contacted the water. So this sort of flash boiling, this is a condition that you actively avoid within nuclear power plants. It's why during any system startup, warm-up, fill and vent, all the procedures are designed such that you open valves slowly, especially across large temperature gradients. One example is the reactor coolant purification system. That is to say, the thing that controls the water chemistry for the reactor. Because you're dealing with water at reactor coolant system temperatures and pressures, you have to send it through heat exchangers to cool it down to from upwards of 600 degrees Fahrenheit down to 150 degree Fahrenheit, so you can do your chemical additions. So across large temperature gradients, yeah, behooves you to have well-controlled valve operation. But yeah, here, water contacting metal that greatly exceeds the boiling point of water will absolutely lead to flash vaporization, steam explosion, and a shockwave. More than enough to shatter an aquarium by itself. This is also something that is modeled in reactor safety because under accident conditions, molten core material can produce these sorts of steam explosions.
You can actually see the aluminum melt here, and notice how it gets magnetically crushed inwards the moment before it explodes.
Yeah.
This explosion was so much more violent than the copper pipe that I suspect that chemical effects played a role. The reaction of aluminum and water is extremely...
That's a good point. So everything I just talked about, that is purely physical. Chemistry has nothing to do with flash boiling, causing shockwaves, anything like that. But this is interesting, too. So you got a couple of things going on here.
energetic, exceeding even thermite by mass.
So, aluminum-water interactions. It's normally inhibited by an oxide layer, which got stripped away in microseconds by plasma. So, that enables the metal to become ionized and hydrogen production to become possible. So, we're approaching the other side of nuclear accident territory physics. Because zirconium, under extreme conditions, and by extreme conditions we're talking greater than 2000 degree zirconium temperature, that rapidly increases its interaction with water and produces hydrogen gas. It's one of the reasons why hydrogen recombiners exist in reactor containment buildings. They essentially run a hydrogen production reaction in reverse. Other choice I've seen at some other nuclear power plants is essentially giant spark plugs, for lack of a better term. After all, you don't want a sudden buildup of hydrogen gas creating a big explosion, so what do? Set off some small explosions, way less dangerous. But this is the extreme worst case scenario post-accident sort of response here. But yeah, this reaction here with aluminum, also highly exothermic. Now, is it more energetic by thermite? Is it more energetic than thermite by mass? I don't actually know. Thermite itself is extremely energy dense and self-oxidizing, but here, especially if you combine both effects, we have both the physical reaction of making the plasma and the chemical reaction. Aluminum water reactions under plasma, yeah, that's going to absolutely amplify it and might even get you the same order of magnitude. I mean, after all, this is plasma, hydrogen generation, rapid steam production and shock waves, and possibly detonation-like pressure spikes in this case. So, yeah, there's a lot going on here, and it's all in the name of increasing the amount of destructive force. That's impressive.
However, this reaction is incredibly difficult to initiate, but I figure a 70,000 amp plasma would do it. I wanted to...
Just like zirconium in the nuclear power plant, I mean, it's not going to interact with water at normal reactor coolant temperatures. You're several hundred degrees too low. And the moderator temperature coefficient is negative, so raising power actually has a feedback mechanism that's going to lower so raising temperature actually lowers power, putting in a natural negative feedback mechanism that prevents these sorts of limits being exceeded unless you try really hard. This is trying really hard.
a better shot of the explosion itself, so I obtained another aquarium and crimped another aluminum cable. It's
going through a lot of aquariums in this video. Usually it's microwave. Well, he's probably going to do something with microwaves later.
A smaller lug that better fit the cable in order to push the explosion to the center.
All right, here we go. Okay, that sounded good.
Unfortunately, the copper lugs exploded before the aluminum here. I managed to push 100,000 amps through this one. But the explosion was less violent than the previous shot, which implies the shot earlier was indeed chemically enhanced.
Sure.
I substantially dialed back the exposure on the slow-mo compared to the last shot, and even though it was the copper that exploded here, the details of the plasma bubble are much more apparent this time.
Yeah, that's cool. Oh wow, look at that.
The last element on my list to zap is tungsten, which is the metal with the highest melting point. This 1/4-inch thick rod may not seem like much, but this is tungsten after all, so there's a sizable mass here.
Here goes nothing.
Yeah, that stuff's dense.
Did it just burn through instantly? What?
Oh!
Alright, this is really strange here. So, it actually just burned and melted the steel around that. There was steel holding it down and it just melted right through that. I think the tungsten did burn a bit, but yeah, it just melted everything else around it. I guess I shouldn't be so surprised.
I mean, everything around it, sure. Tungsten has a melting point north of 3,000 degrees Celsius. So even if you're just talking the steel around it and just a little bit of it, that's still ridiculous power density. I mean, after all, it's 100,000 amps-ish, probably conservative, at about 65 volts, well, at 6.5 megawatts. So even if it's just for a few milliseconds, we're talking tens of thousands of joules being deposited into a relatively small tungsten rod. Yeah, that can raise temperature by quite a bit, and certainly melt off the steel around the sides. Basically, resistive heating at extreme current density. The same sort of thing you use in heat trace circuits for freeze protection around some of the external pipes at a nuclear power plant. The difference is you're missing quite a few zeros in your current draw.
That's pretty funny. Well, I smacked it to unweld it, and it just broke it.
Oh!
Of course, tungsten is pretty brittle, so I'm going to have to get a bigger piece of tungsten here.
Yeah, that's going to be the failure mode.
All right, I've got this long tungsten rod here. So it's a 1/4 inch in diameter. And the thing is, I know that electrically, this isn't a big challenge for these batteries here. This is really more of a materials challenge. All right, so the idea here is that I've added some copper under the this tungsten rod here. And then I'm going to use these graphite blocks to hold it down with the clamps. So yeah, hopefully this works. I'm starting to worry that I'm not going to be able to pull this off. But this should at least make a lot of sparks. So let's try this. All right, here we go.
There's a lot of sparks.
Oh yeah, it completely detonated. Oh yes, it completely detonated in there. Wow. Completely obliterated it. So let's see what the remnants look like here. Look at that. That's true melting.
Okay, that's
happened so fast that it definitely wasn't burning. It actually straight up melted the tungsten.
The slow-mo of this shot is one of my favorite.
Again, over 3,000 degrees Celsius to do that to bulk tungsten.
From the entire video. The white-hot rod gets magnetically shattered into pieces as it melts, sending a shower of burning fragments upward in a scene that resembles something from the Hubble Space Telescope.
Yeah. Okay, so now we're getting into MHD type instabilities that you talk about in Z-pinch plasma physics, which makes sense. We've already talked about Z-pinch. So MHD, that's magnetohydrodynamics. So you got molten liquid tungsten, which is just funny. It's not a typical failure mode you associate with tungsten. So current's going to keep flowing through that. And the magnetic pinch is going to compress that liquid. And then you have the instabilities, the same sort of sausage and kink instabilities you talk about in Z-pinch fusion reactor. So he's demonstrating this on molten metal. That's interesting. I never would have guessed right off the top that we'd have this many comparisons to things that happen in fusion. Albeit, I mean, no fusion's actually occurring here, but the same sort of MHD concerns that you talk about with currents that are typically used in things like national labs for physics experiments. So why not do it in your backyard?
All right, so you can clearly see that that definitely melted there. So, I mean, and it happened so fast that this couldn't possibly just be from burning. You can see how it liquefied there.
Yeah.
I might try zapping these pieces in parallel to see, maybe get a better slow-mo shot.
Okay. Flares, fireworks.
Holy heck. I dialed back the exposure a bit compared to the first shot, and yet, this one ended up even more overexposed than the first. I really should have expected this with twice the metal though. Not only did it melt, it was splashed upwards there.
Oh, wow.
Man, I wish tungsten wasn't so expensive, because I'd love to throw just a huge chunk on here. I ended up splurging on this half-inch
Yeah, have your sponsor give you samples in addition to batteries.
thick rod of tungsten. Once again, this may not look like that much, but it weighs nearly 1 kilogram. To put that in perspective, this thing weighs more than a typical fox squirrel, which is North America's largest species of tree squirrel. The thing is, though, melting
I love how he brings wildlife into his videos a lot.
this rod in air felt like it wouldn't even be a challenge. Of course the batteries could do it. I wanted to melt this rod underwater. This meant I had to come up with some clever mounts. Even though copper melts at a far lower temperature than tungsten, I figured that with enough contact area and a big enough current, the tungsten would still melt even if the full contact area of the copper melted first. The only issue with a full liquid metal conduction interface is that nothing would stop magnetic forces from blasting the copper plates outwards. So, I loosely bolted the plates to a block of phenolic. That way, as the copper melts, the magnetic forces will twist the plates in a way that exposes the tungsten to more solid copper. I couldn't find any more aquariums in the woods, so I had to start buying them at Walmart. The setup of this took so long, I would be very disappointed if this does not work.
All right. Oh man, I'm nervous. Okay. All right, here we go.
Oh, wow. The blue smoke.
What happened? I don't even know what happened. Oh, it's totally gone. What happened here? I didn't hear like this big explosion, but I just heard like this boiling. The scope makes it look like it melted instantly. I don't see the tungsten rod. I don't know what happened to it, and it clearly exploded. So, yeah, we'll find out once this is done saving. That's really strange.
There's a lot to unravel in this footage, so I'm going to start with the real-time views.
Oh yeah, look at that.
Let's start with the obvious. The tungsten was blown to pieces as well as the aquarium. However, did you notice that crazy blue smoke? The submerged piece of white-hot tungsten reacted with water to make this ridiculous mixed suboxide. I had no idea tungsten could make a blue compound like this. When the water drained and this piece was exposed to air, it then burned with the typical yellowish smoke associated with this trioxide. Another important
WO2 and WO3, things that don't really come up that often.
detail is that the cables feeding the aquarium Z-pinched so violently that they nearly uncrimped themselves.
Wow. All right. I have a feeling that every nuclear accident analysis engineer needs to see this sort of stuff because you're having it underwater. I mean, I know there's nothing nuclear here per se, but it's high temperatures, flash boiling. These sort of worst case scenario conditions are being done minus the nuclear fuel and radioactive material. But as far as the effects you see on metal and effects you see on water, they're very much represented here. I wonder if we got some hydrogen formation here as well. I mean, again, back to the zircaloy water reaction at high temperatures. That's where the hydrogen explosions in Fukushima came from. So here, similar sort of territory. He just changed the metal.
Now for the slow-mo. The current in this shot quickly rose to 100,000 amps, producing tremendous magnetic forces on the cable loop feeding the rod, and it was these forces that shattered the aquarium. It took a full 1/10 of a second for the tungsten to melt after the aquarium first broke, and since the view is so obscured by water at this point, I can't say for sure whether it actually melted underwater. Chances are better than not that some part of it was exposed to air, though.
Sure, but even some melting is still, I mean, like in post-accident nuclear studies, I mean, not all of it is going to be a molten pile. I mean, some of it melts, some of it doesn't. I mean, after all, this wasn't a deliberate experiment to melt something. But yeah, these magnetic forces. So force, again, is going to be proportional to current square. So 100,000 amps. That's going to repel those parallel conductors. The geometry is not going to stay perfectly because we have the thing tearing itself apart. So you're going to create a bunch of lateral forces. And again, this is why generator bus ducts and power plants are braced for fault currents. Same thing with electrical switchgear. Have fault ratings, and they're going to be less than this. So going beyond many industrial switchgear ratings with improvised hardware. That's that's definitely something.
Yeah, the Lorentz forces were too strong, it looks like. It's so hard to avoid those huge forces just because the cable has to bend when it goes in there. You know, if I had time to redo this again, I would replace 2 of the edges on the aquarium so I could, with like, on a wood or something. That way I could pass the cable straight through it. That would save a lot of the forces. But I guess for now I'm going to have to call it quits.
At this point, I decided to revisit the magnetic pipe crushing experiments. Even though I had already managed a hot pipe crush earlier, I wanted a better slow-mo shot of that happening, so I repeated the trial with another unfused pipe. However, it failed to crush. The new switch was way too slow to crush even a melting half-inch pipe. With the switch before this, the current would quickly ramp up to 100,000 amps, even if it bounced afterwards. While this new switch can actually close, it can take a full 1/10 of a second to reach full current. That's
Okay, and there's your design trade-off here. Because, yeah, his goal is to crush without melting. So you're going to need very high peak current with very short rise time. And you're going to want to maximize your DI over DT, I being current.
way too slow. I moved up to bigger size pipes for the next trials. I didn't have any cable that would conveniently crimp to this size of pipe, so I just smashed the pipe ends flat with a hammer. The idea with the bigger pipe is that it would allow the current to rise to a higher value before the pipe melts, although it comes at the cost of requiring even higher current to achieve a given magnetic pressure.
Yeah.
Unfortunately, even this did not lead to the pipe crushing.
You're dividing by too big of a time. In other words, yes, it's too slow.
Then one day I had some friends over and I stuck a pipe on the contacts, just with the intention of making a loud bang for them. The switch decided to turn on quickly for once.
What was the second one?
I had some friends over just that is awesome.
So usually because the switch is slow, so you heard the switch go and but something was magnetically ejected. I don't know what. Something got thrown.
That was good. Got
Woo! Yeah, look at that. Completely, totally crushed.
The pipe was crushed so violently that it folded twice.
Nice.
It's too bad I didn't set up external lighting for the slow-mo camera, since I would have liked to have seen more detail here. The magnetic field managed to suck in some nearby steel plates and toss them into the yard. This sent me on a wild goose chase of catching this effect in better lighting. Naturally, the effect turned out to be super difficult to repeat, as the switch returned to misbehaving and turning on too slowly. I was determined to get this to show up on camera though, and blew up more pipes than I'd like to admit in pursuit. The switch wasn't always the failure mode in every shot though. Sometimes the C-clamps would give way, and other times, steel objects nearby would get sucked in magnetically and photobomb the shot.
Yes, magnets causing Photobombing. That is awesome. But yeah, magnetic pressure builds faster than thermal diffusion. And this is why like pulse power systems use capacitor banks, pulse forming networks, and inductors. Batteries are not the ideal case for big DI over DT. High energy, but not high pulse power optimum. So a lot of internal resistance and inductance going on here that he's fighting.
Crushing the pipe flat did turn out to be somewhat repeatable. And if I hadn't seen the cool double fold earlier, I would have been quite content with this. However, I figured that with enough trials, the odds would be in my favor for the double fold to happen again. After countless trials, I finally got the lucky shot I was waiting for.
Determination right there.
In hindsight, I think the trick was placing the pipe on the edge of the blocks, as this intersects a stronger external magnetic field than zigzagging the pipe through the middle. This adds additional lateral forces along the full length of the pipe that help initiate folding. I didn't stop there though. I still wanted to crush a pipe without melting it, and came up with an elaborate plan to do so. For starters, I suspected I could bypass the log splitter switch by using an SCR to slam on the circuit. Of course, I didn't expect the SCR to survive this, but if it...
Yeah, nuclear plants, those are generally used in controlled power systems. So, not sure what this is rated for, but maybe a few thousand amps. But at 100,000 amps, yeah, it's going to explode. But he knows that. I'm sure it's intended to be a sacrificial component.
worked for a single shot, that would be good enough. I also upgraded the pipe from the hardware store variety to oxygen-free high-conductivity copper. The reason being is that at liquid nitrogen temperatures, it's 10 times more conductive than copper at room temperature. This allows for significantly more time for the current to rise before the pipe melts. Now, I close the main switch. That is not touching. Okay. Now, I hit this. Go. No, I missed it on the camera! Heck.
Oh,
No!
Man.
Ah!
That's frustrating.
I had been struggling with my slow-mo camera getting EMP'd, so I removed the trigger cable prior to this. I forgot that this changed the trigger rules on the camera, and pressing the record button didn't actually start the recording. Okay, so, man, it's too bad I don't have data from this shot, but it did pinch a little bit, but I think the most intriguing part is that it uncrimped itself, so this cable probably got, crushed, and then it pulled itself out there, so it pulled out the crimp. That's pretty wild, because I really crushed it down with a hydraulic crimp. So, there was some pinching, and there's a little bit of crushing, but man, I just wish I had the data from that shot. That's a real shame. I decided to give this setup another try with a much more aggressively crimped pipe. I'm going to hit the camera and detonate it, right? Okay. Okay, what happened? Didn't even see any of this. Let's go look at the slow-mo. I did actually manage to capture slow-mo of this one. It's interesting how the SCR in this shot exploded, even though the one prior to this did not. Of course, the first one was still destroyed though.
Yeah, they're not used in 100,000 plus amp systems. For that, you're going to want to use things like vacuum interrupters. This is well beyond semiconductor survivability limits.
Well, looks like it's the SCR that failed there. So, yeah, didn't quite work. That fuse is still totally intact. It had a peak of a little under 100,000 amps, but yeah, I couldn't make it any higher than that. I wonder how much of that was the SCR's fault versus other heating in the circuit. But yeah, disappointing. At this point, I had to admit defeat with the cold pipe crush, because there are still so many more experiments left to do. The cold pipe crush could probably be done with a pulse-forming inductor, though, or
Yes.
maybe just another 400 car batteries. I want to do a brief section on zapping auto parts.
I did like the bit with the liquid nitrogen and the copper, though. I mean, conductivity is going to increase significantly at cryogenic temperatures, though I wasn't really sure what was going to happen there. But lower resistance means slower heating, more time for current to rise, which ultimately would mean a greater chance of crush before melt. I mean, similar things are done for magnets in tokamaks and fusion reactors, trying to achieve superconductivity here, or at least more conductivity.
Since this was a popular request for me. An ignition coil seemed like a good place to start. In the past, I've abused ignition coils to pull off some cool high voltage tricks. With the batteries, though, the internal coil melted too fast for anything interesting to happen. I figured that a starter motor would be more durable than the ignition coil, since it's designed to draw a significant amount of current in operation. Something tells me it isn't quite rated for the full 400 car batteries, though.
All right, here we go.
Yeah, I was going to say, what's the rating on that? Maybe a few hundred amps, if even?
That was lame.
Slow-mo shows that the motor did start to spin, but it
Yeah?
still only managed to survive for mere milliseconds before burning up.
Now I'm just gonna try shorting it through the case. I feel like this should make more sparks this way at least.
There you go.
Ah, yes, much better. I have this long-dead car battery here that measures 0 volts and will not take a charge. I'm curious what will happen by zapping it with the batteries.
You know, I feel like containing this one wouldn't be such a bad idea. I'll
There you
play
go.
it safe with this microwave casing.
I knew it. I knew microwaves were going to show up at some point. They just have to with Styropyro.
Here we go. Oh, jeez. Can't tell what happened. No?
This was one of my most surprising experiments. It looked as if
Good use of a respirator there.
nothing happened, but instead of exploding, this battery was actually revived somewhat. It seems the plates were
Interesting.
desulfated because the battery can now take and hold a charge. That's wild.
You know, jumper cables work pretty well with
That is fascinating. I mean, the high current pulse broken down the sulfate and reformed the plate surface. I mean, there are commercial desulfation pulse chargers. He just did it with a multi-megawatt hammer. I mean, when all you have is a hammer, right? This is interesting.
one car battery, so of course I wonder how well they'll work with 400. I wonder if they'll melt first or if they'll magnetically rip apart. So I guess there's just one way to find out.
Gonna guess melt. Let's see.
Oh hey,
Could be
I was
wrong.
not expecting this. Oh, you're gonna be a problem because I can't blow things up if you're here. Are you gonna interfere with my car battery?
Oh,
My squirrel friend Ophelia decided to visit, so I had to wait to test out the jumper cables. She's used to all the explosions at this point, but I figured I'd let her chew on these antlers in peace before blowing anything up.
very
After a
considerate.
subsequent splooting session, she ran off and I was able to continue with the jumper cable test.
So here's
You know what? That's good. Make sure the area is clear of all personnel and other life forms before you do the experiment. I appreciate that.
the jig for the jumper cables. So I'm just going to, I just have them short of there, just to see what happens there. So we'll see what breaks off first.
Here we go.
What? The switch is closed.
Oh, well, there's the culprit. It melted through the, I guess where it was crimped to the
Oh,
clamp
okay.
there. Well, if these clamps are just going to melt off, I at least want to see what the actual cable does. So now I just have the bare cable against the
Bare
block.
cable.
Here we go.
A little bit of fire.
Alright, so this is kind of sus. Get that in focus. Look how, look, it's silver colored. Is this like copper plated aluminum or something? The box said it was pure copper. So that is,
cheap cables.
that's not pure copper. I don't like that. I think this is just garbage, garbage jumper cable.
I ended up making some much nicer jumper cables using 4/0 copper cable.
Nice.
Alright, this is what I have for the new jumper cable setup.
Maybe these will survive melting, so they'll be affected by the magnet more.
So, have them actually bolted together there, but you can see how that is glued together there. So that's really what I wanted to show. Alright, am I ready? Yes. Oh yeah, they got obliterated. They got obliterated. Nice.
Obliterated.
This was exactly what I was hoping to see. The huge currents traveling in opposite directions through the cables
repulsive
caused
force.
tremendous magnetic forces that ripped them apart.
Nice.
I couldn't get this to happen with the garbage cables I zapped earlier because they melted before passing enough current. The final auto part to zap is the suspension spring here,
Ooh.
and I did this one with an audience.
Are you guys ready?
Yep. Nice.
Alright, here we go.
Oh, that's fun.
Heck. This suspension spring ended up as one of my favorite shots of the whole project, and for such an ironic
Steady
reason
heat.
too. The long length of steel acted as a resistor and substantially limited the current, starting at only
Even kind of looks like a resistor that you see on electrical drawings.
8,000 amps and dropping to less than 1,000 by the time it melted through.
Okay, thus far this is the one that behaved the most like a nuclear reactor. No instant explosion, just some steady heating, resistive heating. After all, a nuclear power plant's fuel rods are designed such that heat generation is high, but temperature rise is controlled. No runaway. I mean, yeah, look, this thing still caught fire and everything, but compared to all the previous experiments he's done thus far, this one, I can see why it's his favorite. It's very controlled.
It's usually all or nothing with these batteries. Either the items are obliterated in milliseconds, or nothing interesting happens. It was cool to see something that fell in the middle ground between these two categories. Later on, I zapped a length of chain that gave a similar middle ground result. In this case, the chain
nice.
reached a steady state where it got red hot but never melted through. Other than this chain and the suspension spring though, everything else I zapped either instantly exploded or had no visible reaction.
Whoa!
I was not expecting anything he experimented on this to have a slow, steady burn sort of thing, at least relatively speaking, when you're talking about 400 car batteries out here. The amount of current, heat, and magnetic forces we're talking. I mean, after all, this is closer to pulsed fusion driver experiments or railguns or MHD labs or severe nuclear accident simulation. I mean, it's fascinating, like pulsed power physics through brute force experimentation. Normally the sort of thing you'd see where utilities would do arc flash boundaries and national labs build these reinforced chambers. And nuclear safety engineers start modeling hydrogen gas buildup and so many other things. This guy mentioned he used aquariums from Walmart, which is awesome.
The next experiments, I've hooked the output of the car batteries up to this metal stick here, mainly because I want to try cutting stuff with it.
He's got some more PPE.
Now, I did some experiments like this in the last video, but with this one, I'm most interested in testing different electrode materials, because I can already tell you that this steel electrode here is not going to last long. So yeah, let's get to experimenting. Now, I'm going to have to step up the PPE for this section. In particular, I have this arc flash hood. Now, this was actually given to me by Greg Lay. And if you don't know who he is, he recently had a lot of notoriety for his Lorentz cannon video that he posted. Now,
Oh yeah, I like that one. That one was a lot of fun.
I actually find it hilarious that this is the video that got him so much notoriety, because that's really like a tame project for him. He's currently building the biggest Tesla coils ever operated right now to do some just ridiculous lightning experiments. So yeah, that guy is the man when it comes to electricity. So if you don't know who he is, you should definitely check him out.
Oh, I have. Yeah, he's also a legend.
And yes, a big thank you to him for giving me this arc flash hood.
That says 100 calories. All right. I mean, he's getting himself ready for arc flash hazards that you would see in substations or switch yards at a nuclear power plant. I mean, 150,000 amps, even at 60, 65 volts, you're still going to be in utility fault current territory. At the plant I worked at, there were 480 volt, 4160, and 13.8 kV volts AC switchgear, and everything in those rooms are arc flash rated and seismic rated. And their electricians and plant operators, when they would rack the breakers, would dress out in 40 cal suits. And when I say cal, if you're unfamiliar, it's not quite the same as the calories used to measure energy in food. It's arc flash incident energy. It's actually calories per square centimeter. So yes, and he's producing a lot more peak instantaneous current than those plant operators or electricians would be exposed to potentially in the switchgear room. So I can understand why the 100 cal arc flash hood, when he's essentially performing uncontrolled DC fault testing with a lot of current in his backyard.
And yes, a big thank you to him for giving me this arc flash hood.
I'm gonna keep this section short because between my respirator and arc flash hood, it sounded like I was speaking through a wet sock on my microphone. I would like to take a moment to appreciate the sparks.
Yeah, and when you see people do these sort of operations in a nuclear power, well, you're not going to see anyone causing these sorts of arcs on purpose, but it can be pretty challenging to hear because you also have hearing protection on underneath them as well, because it's typically in a high noise area. Just to add to that, switchgear rooms can be quite loud because of all the fans
that iron makes, not only here, but throughout this whole project. Iron sparks aren't nearly as bright as many other metals, but this fairly subtle effect pairs nicely with the extreme powers I have available.
like the grain.
Plus, when it comes to filming these effects, it's much easier to capture something like iron sparking compared to a bright metal like magnesium. Honestly, iron is an underappreciated element overall.
You know, I think of those memes where they said,
Maybe in modern times, I don't know, pretty sure there was a whole age of human history dedicated to iron.
this is why women live longer than men. Yeah. That was fun.
Yeah, this is exactly how plasma arcs behave in reactor switchgear faults. These iron sparks, molten iron droplets oxidizing in air, and the magnesium sparks, chemical combustion plus arc heating. And again, an arc is not just electricity jumping. It becomes ionized metal vapor in a conductive plasma channel that is thermally self-sustaining. Again, that's why everything in switchgears are arc-rated and compartmentalized. You don't want to have too many switchgears right next to each other. Each train of safety-related switchgear equipment is in a different room, sometimes on a different floor in the building, the electrical auxiliary building.
Now, I want you to notice those curved paths there. I felt this, force off to the side when I was trying to cut there. I think that was being magnetically deflected. It was really strong too. All right, now
That's definitely the Lorentz force. I mean, we're talking 100,000 plus amps. Yeah, that magnetic pressure is enormous, as we've seen earlier in these parts. And that's why mechanical bracing is needed for these fault forces in switchgear cabinets, because these bus bars can literally jump with these very strong Lorentz forces.
upgraded to a magnesium electrode this time. Now,
All right.
magnesium doesn't have a very high melting point, but it is surprisingly conductive, and most importantly, it's very pyrotechnic. So I'm curious to see what happens when I try cutting iron
Yeah, you use these a lot in fireworks.
with this magnesium electrode here. Oh dear.
Yep, fireworks on the ground.
Right off the bat, it was clear that magnesium was an entirely different animal. Since magnesium burns so readily and energetically in air, these chemical effects greatly enhanced the heat
Yep.
produced in the arc. It didn't take long to ignite a good portion of my yard on fire with these scenes. The most dramatic difference compared to iron was how hard it was to hold the magnesium electrode. It was extremely difficult to make more than a brief contact, since the electrode would get forcefully ejected from the object I was zapping. The magnesium was obviously drawing more current here. Now, one interesting thing I do want to note is that the magnesium here didn't get that warm.
So even though, you know, it just produced just incredible temperatures there, what happened here, it just, because it's so conductive, it really didn't get that hot. It wasn't on fire, so I dumped some water on it, and it even like sizzle.
So that's an interesting observation. And that's because the energy deposition with magnesium is going to be very localized. Heat is simply dumped into the plasma channel, and the electrode bulk mass, well, that's going to be your heat sink. Kind of like how fuel rods and reactors have high surface heat flux, but relatively low overall temperature due to the presence of the reactor coolant. So we're by no means talking about a low energy system here. It just means the energy transfer dynamics are going to be a little different.
Now this is the one I'm most excited for. It's a big rod of titanium.
Ooh.
Now titanium has a, it's more resistive than the magnesium is, which honestly is probably going to be a good thing, but also has a very high melting point, and more importantly, it's still very pyrotechnic. So yeah, I'm going to hook it up to that stick over there and try it out.
Okay.
I would say that titanium was my favorite of the 3 metals I tested. It was far easier to hold the titanium electrode compared to the magnesium one, likely due to its much lower conductivity limiting the current. Even with the lower current, I'd bet that the average power was still higher, simply because I could actually hold the electrode in place and get a faster train of pulses compared to what I could with magnesium.
The difference between sustained power and pulsed power. Like anything involving pulsed power, you can have some pretty impressive power numbers, but they're not sustained. Like those handheld pulse laser tattoo removals, which Styropyro has demonstrated with this. Yeah, you could technically say you have megawatts in your hand. Well, that's because power is energy per unit time, and there you're just dividing by a really small number. Sustained megawatts, say, on a big diesel engine that provides those sustained megawatts to all of a nuclear plant's emergency backup systems. That's a more impressive display of megawatts and ultimately more energy being produced.
Titanium's high melting point also meant that this electrode lasted much longer than the others.
Look at that titanium rod. I didn't even realize it was getting so hot. Yeah, it's clearly more resistive there, but I can't believe that. But wow, that one is fun. That is very fun.
It almost looks like it's made out of plastic, just a piece of red plastic sitting on the ground, and then you get close to it and realize how hot it is.
There's an old saying that says that anything will act as a fuse if you put enough current through it. I feel like most of the experiments in this video will fall under that. However, I do want to try popping some like actual legit fuses with these batteries.
Okay.
In most other scenarios, a 500 amp fuse would seem pretty huge, but in this context, it's pretty tiny. What happens when I zap it with the battery?
Yeah, it's pretty small when you exceed it by 3 orders of magnitude here.
All right, here we go.
If you thought that was boring, well, it's designed to be boring.
Yeah.
A fuse is supposed to break the circuit in the least exciting way possible.
Yep, it's a protective device, just like any other form of circuit breaker.
I cut open the fuse to see what's inside.
Let me see.
As you can see, it's filled with sand, which prevents it from getting spicy when it blows. Some of the sand actually melted to the fuse element there. Here I have a 1000 amp fuse, and I'm actually going to cut it open first. That way we can at least see some sparks when it pops. This fuse looks to have parallel elements inside. I hope this one is more exciting than the last one.
Well, you took the thing out of the fuse that does the containing. Fuse sand's going to absorb the heat, quench the arc, and prevent these plasma jets from forming. I mean, it's the electrical equivalent of your containment spray system in a nuclear power plant that has borated water to not only provide pressure control and cooling to the containment structure, but also sprinkle a little bit of boric acid in there just for additional reactivity control to ensure the reactor has even more shutdown margin than you would already need to make sure the reactor has more than enough shutdown margin in an accident scenario. After all, subcriticality or shutdown margin is the most important critical safety function post-accident. One of the reasons why Chernobyl was so bad is they had prompt criticality, which is the opposite of subcriticality, and why the status of their emergency core cooling system was ultimately irrelevant. Bit more of a pop.
Nothing to write home about, but that vivid green flash was pretty neat.
Nice.
I can see the burn through there was a lot more complete compared to the last one. That's probably just because I got rid of all the sand inside.
I refilled the fuse with indium metal to see if anything cooler would happen when it zapped.
Okay.
Probably should have done the math on that one because the indium didn't melt at all, so I think there's just way too much cross-sectional area of indium. But look, that the magnetic forces actually bent those tabs there. Those are thick tabs.
Wow.
So that's pretty silly.
The slow-mo shows that the extreme currents may have magnetically ejected the fuse before the indium could melt. Regardless, I doubled up the cable feeding the fuse for the next shot to play it safe.
All right, there we go.
One other thing is less heat is going to be generated from something that is more conductive. In heat trace circuits that heat up pipes in a nuclear power plant during cold weather, it uses resistive heating, where the heat dissipated is going to equal the current squared times the resistance. And well, if your resistance is very low, you're going to have less localized heating in the heat element. So that's one other benefit of having things with high conductivity is it can put you in a scenario where you avoid overheating. But it ultimately depends on what you're trying to do.
Yeah, I don't think there is a drop of indium left in that fuse. That just completely exploded. That's really, really funny. Oh, and there's a bolt there that I did not put that there. That just, of course, got magnetically
Just
sucked
showed
in,
up.
as everything does.
Magnets.
And let's go take a look at the current. 120, 130, 130,000 amps. Not bad.
Nice.
The slow-mo on this one turned out awesome, even though the clamps barely held up for the shot. Most of the indium was ejected as it liquefied, mainly via magnetic forces at first. And then when the fuse finally popped, it made an impressive explosion.
Alright, now it's time for the real inspiration of this section. Some years back, the electricity legend photonic induction popped a 5,000 amp fuse.
Yes.
As far as I know, this is still the biggest fuse that's been popped on video.
I love it. He's referencing a lot of these other crazy videos that I've already seen and made reactions to. And yeah, I can tell all these guys know each other. That's awesome.
Well, I'm going to try popping a 6,000 amp fuse.
Of course.
This monster weighs something like 45 pounds, and it's the biggest fuse that I could find online. Now, it's not often that I can beat photonic induction at anything, so I felt like this was a good use of my batteries.
This monster has silver-plated copper
Takes 400 car batteries to beat photonic induction. Yeah, that's... I forget how many batteries he had in that video, but it wasn't 400.
contacts and has an impressive 200,000 amp interruption rating. That's one heck of a fuse.
Now, of course, being a 6,000 amp fuse means that it's meant to conduct 6,000 amps without popping.
Yeah.
So something like this car battery here, I mean, it could short this car battery all day and it's not going to pop. I mean, it's going to kill the car battery first. So this is where the 400 car batteries come in.
So how much
Gotta work together to break this big fuse, huh?
current does it take to pop this thing? Well, that depends on the duration of the impulse.
Is he gonna pull up the charts?
My 6,000
Yep.
amp fuse is the top line on this curve here. So based on this, at 10,000 amps, the fuse will last about 17 minutes before popping. If you go up to 20,000 amps, it'll last about a little less than a minute. But of course, I'm most interested in this end of the curve. At 100,000 amps, it'll only last 10 milliseconds. Now, of course, the actual peak current that this gets to before it pops is going to depend on how my switch wants to behave. But regardless, this shouldn't be very hard for my batteries.
In the interest of making more sparks, I opened it up and emptied out all the sand
Of course
inside.
he did.
This
You gotta get all that pesky containment structure out of the way. I have a feeling if this guy had a nuclear power plant, he'd get that pesky containment building out of the way first.
does change its fusing characteristics, but I would argue that due to the nature of the continuous extreme DC currents I'll be feeding it, the fuse will now take an even higher impulse before breaking the circuit. The reason being is that without the sand, it's going to make some angry plasma.
Got a fair bit lighter too, I bet.
That's hilarious. It's just a bunch of smaller fuses in parallel. Like that all the way down.
I mean, yeah, do you want to put like one really big one that's like 100 feet long or something?
Down, isn't it? Fuselets all the way down.
It's a lot though.
I'm not even going to bother cleaning the contacts here because it'll melt straight through all that, char and stuff on there. All right, there it is. All the cameras going. Here we go. Let's pop it. Let's see. All right. I think I'm ready for this. I think I'm ready.
Nice.
Let me get my slow-mo camera set up here. Yep, all the cameras good? Think so? All right, here we go.
I'd buy the tree. There you go.
Jeez! I think I popped it. Wow. I can't wait to see what it pulled in the scope there. Oh yeah, big pulse there. Oh, what happened? What? It's not dead. No way. It melted the contact block. It didn't blow up the fuse.
Oh.
That's
I mean, that makes sense. It's going to take the path of least resistance, which is why, like, blocks, bolts, lugs, and terminations are going to be the thing that fail before the bus bars do in switch gears. And that is why a lot of those systems have critical torque specs, because those are going to be the weak points, at least as far as resistance is concerned.
crazy. What? It didn't pop it. What? Look at that. It melted the block first, and it ripped up that C-clamp. There's only
the clamp too. Yeah,
that's insane. I'll just have to resituate that because the fuse is completely intact. Wow, I was so confident that that was gonna
good fuse.
work in one shot too. It's crazy.
Sure enough, the close-ups show that the fuse itself was completely untouched by this. The sparks were simply from the contacts below burning up and causing the C-clamps to give way as a result. If you wonder why I didn't bolt
I love that. It's pretty explosion, but it survived it. Like every major villain in Dragon Ball.
the fuse to the blocks, it's because the blocks are too uneven from previous experiments, meaning bolts would lead to the same results as the C-clamps. This isn't something I can buff out. A suitable clamp, however, will allow the high points to melt, giving a conduction path with very low resistance.
Okay, so I've changed this side to spring clamps. That way it can like follow through as any variations burn out there. So yeah, let's give that another go. Dude, I can't believe that this is taking me 2 tries. This is silly. All right, here we go. Okay, yes, that one finally popped it. Thank goodness. There we go.
Some pieces
I'm
land on
surprised
you
how
behind the
clean
tree.
of a burn through that was. It just completely vaporized
Nice.
those pieces in there. Kind of surprised, just considering the voltage I'm dealing with is low. But that definitely did it. That was a full pop. The switch had a few hiccups there, but once it finally closed, the fuse pulled 150,000 amps. So that is why that was so violent there. Nice.
The slow-mo shows that the fuse made an incredibly violent plasma jet when it burned through. Impressive. One thing I have to mention is that
I mean, low voltage, high voltage. I mean, an arc is an arc at this point. I mean, here you just went way high on the current.
when photonic induction popped his fuse, he used a capacitor bank that gave a short but intense impulse. Now he claims a peak current of 200,000
That's right,
amps.
Now, even though he doesn't provide waveforms, he likely achieved at least that number. Now, when I set out to make this video, I really thought I was going to show you the highest current on YouTube, but that's because I didn't consider his video. And I popped a bigger fuse than him, but as far as the highest peak current on YouTube, he still has me beat. I will say this though, his capacitor bank is very impressive. And although I don't have a capacitor bank like he does, I do actually have a more energetic pulsed electrical device.
No, I'm not talking about the batteries. I'm talking about the cables feeding the batteries, specifically in their inductance. When the bank fires, there's actually more energy stored in the magnetic field around the cables than photonic induction's capacitor bank at full charge. This inductive energy plays a role in the explosions I get when objects burn through.
Yeah, at 150,000 amps, even a small inductance is going to store large energy because, again, it's proportional to current squared and just directly proportional to inductance. That's why in nuclear power plants, generator leads and transformer windings have to account for all that stored magnetic energy during faults. Because after all, what Styropyro has here is basically a pulsed power lab with car batteries.
Now, even though I popped this fuse, I still have one experiment in mind left for it. I want to see how it acts when filled with metallic sodium. Interestingly, when I was considering sacrificial fuses for the pipe crushing experiments, sodium metal stuck out to me as a promising material, since it has a very high conductivity along with a low melting point.
That's just fun.
Yeah, just sort of smash it all in the middle like that. Maybe I can shove it back in.
There was a lot of leftover sodium from that shot, so I smashed it up against the contacts in order to give it another zap.
Alrighty, here we go.
Like belching.
Honestly, these shots were kinda mid. I think sodium's high conductivity actually made it hard to heat up with the batteries. Spraying everything down with a hose afterwards showed that little droplets of sodium had been...
And again, back to the whole I squared R heating is what is occurring. And if you lower the resistance too much, or increase the conductivity rather, yeah, that number's going to go down.
Splattered everywhere, which I thought was pretty funny.
Now it's time for my favorite experiments of this whole project, the magnetic experiments. As you've seen countless times by now, the currents I can pull from my batteries produce incredibly strong magnetic fields. Now, these fields were a nightmare when I was trying to build my switch, but now that I have that somewhat solved, now I can actually have fun with the magnetic field.
A typical electromagnet involves a coil of wire wrapped around an iron core. At the currents I'm dealing with, though, an iron core will just saturate, which means I'm better off not using anything as a core material.
Now the problem is that making even a bare coil is an engineering challenge at these currents. It takes an enormous amount of metal to not melt just instantly, and that's on top of how magnetic forces will try to shred any coil arrangement.
As an example, I wound this coil here with stiff aluminum cable. Its resistance is high enough that it will only pass around 50,000 amps or so.
Oh yeah, scrunchiness.
Even at these limited currents, the coil windings are strongly attracted to each other and cause the coil to scrunch up. At 150,000 amps, these forces would be far stronger.
Yeah, magnetic pressure is going to be proportional to magnetic field strength squared, which is driven by current, so... And this is the same reason why during short circuit testing, bus bars must be mechanically braced. Taken up to the extreme, in fusion reactors, magnetic pressure containment is going to be the primary structural concern. Good old Ampere's law.
A lot of time considering how I was going to make suitable coils without spending a fortune on metal. But after witnessing how anything becomes a magnetic black hole at these currents, I realized that even straight pieces of copper would be more than adequate for these experiments.
Sure enough, by sticking a couple cables on the blocks and tossing a bunch of nuts and bolts around them, the magnetic effects are super obvious.
Gonna see some magnetic spaghettification, maybe? Probably too fast.
Wow,
Wow, look at the exploded cable there.
The switch performed horribly in this shot, but even so, the nuts and bolts were glued to the cable
More magnetic photobombing.
before the current had hit even a quarter of peak. When the cable finally melted through, it managed to catapult some of the bolts across the yard.
I mean, when you have essentially megawatts worth of power, granted on the order of milliseconds here, that's not surprising. I mean, I can imagine the amount of arc flash analysis, fault current study, structural review, seismic review, and protective relays that would be required if you're going to try to commission something like this at a nuclear plant. Yeah, I mean, he's basically doing destructive testing here without the normal protective systems that the industry relies on, which is nothing short of remarkable. I mean, forget just the nuclear industry. Any industry that deals with arc flash, in addition to showing those NFPA 70E safety briefings where they show the arc flash with the dummies, you can look at some of this stuff too. I mean, it's really just the same physics at work here.
One that grew up with a CRT TV is
Oh,
probably
lovely.
aware of the fun that can be had when a magnet is brought
Magnets.
near them. Their sensitivity to magnetic fields is the same effect as all the other magnetic forces in this video. It is yet another example of the Lorentz force acting on current.
Absolutely.
I was curious how much a CRT TV would be affected by the fields produced by this battery bank. The load for this shot is my standard pair of 4/0 copper cable.
I really hope this doesn't kill the TV. All right, let's do this. And here we go.
Wishful thinking.
That had an adverse effect on the electronics in this TV.
Your warranty has been voided, provided you got the extended warranty for a TV that's that old.
The magnetic field was so intense that it just turned off. I didn't know that could happen.
Oh yeah, the CRT looks different after that.
That's good old Maxwell's equations doing their job. So a CRT works by steering an electron beam using magnetic fields. So if you put in external magnetic field, one using 400 car batteries, mind you, you make it strong enough, which this will be strong enough, then yeah, that beam's being deflected off screen, and you're absolutely going to disrupt the internal electronics. So at that distance, on the order of centimeters away, you're going to be in the multi-millitesla to single-digit Teslas, so comparable to MRI machines. You know, those things that say, please remove all metal if you happen to be going into the room. So yeah, in nuclear power plants, any sensitive electronic room talks about electromagnetic interference. I mean, there's a reason why radios aren't even used in switchgear rooms, just from radio frequency interference as well. And this is why safety-related instrumentation and controls cabling is shielded and separated from these really high current conductors. So in addition to nuclear accident analysis simulation, arc flash simulation, can go ahead and add EMI qualification tests to this lovely apparatus he has constructed. That's cool.
I know it temporarily killed it, but yeah, let's take a look.
Yeah, I think that was a bit excessive because the magnetic field was so strong it just completely deflected the beam off the screen. So, yeah, maybe I need to move it away. Yeah, that plasma shield did some work there. Ripped off one of the C-clamps, and then wrapped that cable back. A peak of 160,000 amps.
Oh,
So, pretty intense. You know, I
the highest current reading we're up to now.
think it was a bit much to have the TV in the center there. I decided, I moved it out this time, and I also, I'm going to limit the currents by using this steel rod instead of copper. Because yeah, I think 160,000 amps was a bit much. Then also, now that the field...
Yeah, 160,000 amps. I mean, so force is going to scale with the current squared. So actually a pretty big difference between 160,000 amps and 150,000 amps. That is electromagnetic mechanical forces here. So this is functionally equivalent to repeatedly slamming a generator into a bolted three-phase fault. Except it's DC. Yeah, that's different.
is going to be, the magnetic field is going to be reversing directions here, so maybe we'll actually fix the TV by having it sit out here.
I'm sure that'll work.
Okay, here we
Awesome.
go.
Just thinking like old school TV repairmen bringing out 400 car batteries to, I'm going to electromagnetically fix your TV.
Yeah, that was much gentler that time. That was only about 55,000 amps. So yeah, that was pretty interesting.
Yeah, 55,000 amps is way less because of the square law.
Glad I tried that. Now it looks as good as new.
The image on a CRT TV is produced by an electron beam, and it's this current that gets deflected by the magnetic field. This sort of magnetic beam deflection is actually the basis of mass spectrometry, which is a standard analytical tool in chemistry.
Yep, and in nuclear engineering, that's one of the ways you could tell enrichment, just because uranium-235 has a different mass than uranium-238.
I made an important discovery when I zapped a Z-shaped cable.
Oh,
My
Z-pinching.
intention was to physically simulate the forces and torque present on my Z-switch arrangement. The clamps ended up failing on this one, and it functioned as a magnetic catapult. If you look closely, cable fragments were ejected so quickly that it managed to do a little tree trimming out in the distance. The slow-mo shows a lot of cool details. A bunch of magnetic junk got sucked in like in every other shot, but in this one, a little magnetic particle managed to orbit the cable for a bit. The main takeaway from this shot, though, is that the cable is bent from its original arrangement and violently ejected upwards. I stuffed the cable back in the blocks, but this time, I bent the cable so that it was below the center line of the currents feeding it. The switch struggled to close in this one, causing the cable to bounce around for a while at first, but the main result was clear.
I love the floating particles.
It was being violently slammed downwards this time. A bonus is that when the fuse in the center finally exploded, it ejected a neat ring of liquid copper. These shots gave me an epiphany regarding the mysterious forces that eject the cables from the blocks. I thought I had solved it earlier, in that the fields from the straight current through the blocks was causing this. But no, that's completely wrong. Those fields do exactly the opposite. They actually pulled inward via the Z-pinch effect. That means that this mysterious, tremendously strong outward force is actually beating the fierce Z-pinch forces that pull it inward. What's actually going on here is quite profound. I've had to read a lot about fusion power for this project.
Nice.
Because I'm dealing with fusion levels of current.
Minus a couple of orders of magnitude, but if you're talking the low-scaled tabletop fusors, maybe.
And the people in this field have done a good job at documenting the just crazy things that happen at extreme currents. Now, sure enough, the same phenomenon that launches items in my
Gonna bring up sausages and kinks.
setup is actually a huge issue in fusion reactors. So here's the basic idea for what's going on. So when a current path is perfectly straight, that means that the magnetic forces that crush inwards are also perfectly balanced. However, this is an unstable equilibrium. If there's any sort of bend in this current path, then you get this buildup of magnetic field on the inside of the curve compared to the outside, which causes a net force pushing outwards. Now, of course, this makes the current path make an even bigger bend, which means you have an even bigger force pushing outwards, and you get this runaway force, and this effect is called the kink instability. Now, in my setup, the fact that the current has to make this small bend off the blocks is actually the origin of this incredibly strong force that launches my items. And
All in all, a pretty good explanation. I mean, he would have to know his stuff in order to do this type of experiment. But yeah, like you said, straight current path, inward magnetic pressure, Z-pinch. Small bend gives you asymmetric magnetic pressure, and that asymmetry can give you the runaway outward force, the kink instability. And yeah, in tokamaks, Z-pinch fusion, anything dealing with high current plasma, and when I say high current in this case, talking millions, maybe tens of millions of amps. Though in fusion, plasma is not mechanically clamped like copper. Just thought to make that one clear. So once kink instability grows, confinement is lost, and there goes your fusion reaction. Not talking anything extremely dangerous, like in the event of like a meltdown or anything like that. It just means, hey, you don't have a fusion reaction anymore. But ultimately, the physics is the same. Again, the difference is in fusion, you have millions of amps, extremely high temperature plasma, so hundreds of millions of degrees, and there is no solid structure to suppress the instability. So he's seeing a mechanically amplified version in solid metal.
just to clarify this insanity, simply making the current take a 1-inch jump off the center of the blocks produces forces so strong that it can rip up 4 8-inch C-clamps that have been wrenched down so hard that the handles are bent. That is the nature of extreme currents for you. Now I'm lucky in that my current path is through a solid conductor, which means I can just add more clamps or maybe pound the ends flat first to defeat this force. Now when the conductor is a plasma like in fusion, this is much harder to deal with. In fact, it's instabilities like this that are one of the main obstacles to achieving fusion power. In order to mitigate the kink instability, I started using leftover pipes.
He's right, I appreciate him reading up on fusion.
From the crushing experiments as loads. By pounding the ends flat, I can mount them closer to the blocks than the 4/0 cable, and the rigidity helps prevent runaway forces compared to the flexible cable as well. For this shot, I sprinkled a bunch of magnetite under the pipe.
Nice.
I was disappointed when I had to concede that I couldn't get a perfect turn-on with my switch. But in many of these experiments, the initial chaotic changes in current honestly make for cooler video. In this clip, an initial brief pulse launches some of the magnetite beyond the pipe, and this happens once again before the switch finally latches shut. If you look closely, you'll see that the magnetite spirals inward as opposed to traveling straight to the pipe. The coolest part of this clip is after the pipe explodes and the magnetite rains down here in this crazy pattern. I think what's happening here is that the magnetite was magnetized by the current, and this residual magnetization causes the particles to clump up and stick together. I wanted a better slow-mo shot of bolts getting sucked into the magnetic black hole of all this current, so I repeated this experiment using a pipe fragment as the load.
Ow.
Whew! Alright. Beautiful.
Unfortunately, both C-clamps failed to hold down the pipe in this one, causing a bunch of sparks to obscure the view. One of the C-clamps was completely destroyed here as well, since it briefly conducted some of the battery current. I used a longer pipe for the next shot. That way I could hold it down with 4 C-clamps instead of 2.
I will never get tired of him just hiding behind this tree. Safety grade tree.
This could be an epic one. Let's see how this one went. Oh yeah. That was awesome. Cool. Yeah, it was awesome. That was a good shot. I couldn't tell where it went, but that's just because it got slapped backwards there. And all those bolts just went everywhere. Yeah, it looks like a peak of 160,000 amps on that shot.
And just the field gradient force being generated here. So you're seeing all these ferromagnetic materials getting pulled in, circling around, and latching on to the pipe. I mean, field strength is highest near the conductor, so objects are going to accelerate to the region of strongest field. And this is why nuclear power plants restrict loose ferrous tools near strong field areas, such as generators. And this electromagnet's more powerful than a lot of lifting magnets for a few milliseconds.
Switch had some issues, but hey, it did its job. Sorta.
This is one of my favorite shots of the entire video. The bolts were quickly sucked in by the current.
Yes.
And the oscillatory nature of the startup is once again apparent here. It's clear that it's not just the bolts getting pulled in by the field though. A spring clamp on the ground found its way to the pipe as well. And even way in the background,
look at that.
You can see everything magnetic getting thrown around. The pipe eventually collapsed by the forces of the current it was carrying, and it made a hefty fireball when it finally melted through. I wanted to see if I could hit a weight limit for the lifting forces, so I placed about 10 pounds of big bolts all around the pipe for this shot.
10 pounds of bolts.
That didn't sound good. I don't understand what happened. What? That's weird. They all got sucked in and glued to it? What? That doesn't make any sense.
Did he make a sculpture?
What? That's so weird. I've never had that happen.
This one was unusual in that the bolts didn't fall back down afterwards. They were stuck to the pipe.
Made a sculpture.
No, this is really weird. So the pipe got pulled downwards and these are all like glued to the pipe. They're all welded together.
The slow-mo shows that the nearby bolts were effortlessly sucked in by the magnetic field, and less than 1/10 of a second later, the bolts that were out of frame on the ground got sucked in as well. There was so much iron getting pulled in and accumulating on the pipe that it eventually spanned the entire gap between the blocks, which meant that it too began directly conducting some of the current. This current welded all of the bolts together and around the pipe, so this is why they didn't fall off afterwards. The biggest iron object I had that would fit between the blocks was this anvil. It weighs 10 kilos or 22 pounds, so it's a hefty little piece of iron.
I'll never get tired of him just smashing stuff for... Well, I'm not actually sure why, it's just funny.
Iron.
Alright, here we go. It sounds like the anvil got zapped.
Yep.
It never stops being crazy to me that the strongest electromagnet I've gotten to screw around with on video isn't a big coil of wire around an iron core, or even a coil at all. It's merely a straight piece of copper that just so happens to pass an entire thunderstorm's worth of charge in a couple tenths of a second.
Causes an anvil to jump and do a somersault on top of it.
Much like the big bolts before this, the anvil was pulled up against the copper blocks, causing it to pass some of the current as well, which is the reason for the sparks. I want to point out something surprising about the dirt on the blocks here. I know countless commenters are going to lecture me about dirty contacts increasing resistance and causing problems, but I found that the max current is completely unaffected by whether I clean these or not. Where contact resistance actually matters is in all the little cable connections throughout the bank. Those have to be spotless to get the currents I'm achieving. However, I found that anywhere the current density gets extreme, like the
probably cutting out, making him checking all the contacts between the individual batteries.
Blocks or the switch, the contact interfaces actually melt, giving a purely metal conduction path that has extremely low resistance. If anything, the dirty blocks help the switch close faster because the current initially ramps up slowly. Pretty weird, right? Notice how they're pointing all over the place at the start here. This is because of the pieces of iron nearby that have been magnetized from the previous experiments.
Jeez. Where'd it go? Where'd the pipe go? I have no idea where the pipe went.
Awesome.
Here it is. Oh, it got crumpled like crazy. Look at that. Wow, it really folded in. That's impressive. That was one of my best crushes.
I nearly didn't include this compass bit in the video, because what the compasses show doesn't make any sense. In particular, the 4 compasses on the side of the block to the left read alternating values. And that's ridiculous. They should all be aligned with each other. I initially chalked this up to the compasses being cheap garbage and simply reading incorrectly. The pipe crush at the end was so good though that I wanted to include this clip in the video. I decided to give the compasses the benefit of the doubt. I grabbed my box of new compasses and tested them with a magnet. Much to my surprise, they all tested perfectly. That's strange. I had kept the compasses used in the experiment separate since they were dirty, so I grabbed that box and tested them. Lo and behold, some of them read exactly the opposite of what they should. What gives? A compass works on the principle of a magnetized needle aligning itself with a magnetic field. It seems what happened here is that the magnetic field became so strong so suddenly that the compass needles that were initially aligned against the field didn't have enough time to reorient and were remagnetized in the opposite direction.
That is impressive. Producing a pulse strong enough and fast enough to reorient domain. Alright.
That's pretty neat. I had noticed that these pipes have been acting as decent catapults, so I wanted to try intentionally launching something this way. I glued a big steel nut to this GoPro here, and notched the pipe to cause it to melt through in this location.
Yep, we're good. All right, here we go. Where'd it go? Oh, it didn't get launched. Well, it did not get launched into orbit, it looks like. Sad. A little crispy, too.
The inertial forces were too strong, and the nut was immediately ripped off the GoPro. The nut was catapulted into oblivion, but the GoPro barely moved. I ended up bolting the nut to the GoPro in a very ironic way in order to give this another try.
That's awesome.
It did get launched.
It wasn't launched as far as I'd like, but I am impressed how well it held up to the magnetic fields. I've had major issues with my cameras getting EMP'd throughout this video, and that's even with them spaced much further away from the big currents.
That I'm honestly surprised by, because we're talking large DI over DT, induced voltages, and radiated EMPs. It's the reason why sensitive instrumentation in a nuclear plant is shielded from lightning strikes, switching transients, fault-induced EMI, anything that can cause something like that.
The time has come for the final experiments and my favorite shots of this project.
Ferrofluids?
I'm going to see what happens to ferrofluid next to a pipe carrying 160,000 amps. Ferrofluid is a neat way to visualize magnetic fields, and it consists of magnetic particles suspended in a fluid. Most demos showcase it around permanent magnets, but of course, it works just as well around electromagnets too. Considering the strength of the fields I have available, I expect this one to be pretty cool.
Woo! Something exploded. Oh good, the pipe crushed.
Ooh,
All right.
something exploded.
That was cool. Let's see what that looks like. Oh! Holy! That was an epic shot! Wow! Wow! Okay.
I didn't realize that the dark background wouldn't offer enough contrast against the ferrofluid to see it rise up, but at least the fluid wrapping around the pipe was super obvious. I want to point out the bit of ferrofluid that gets trapped around this little iron post, and that's due to the iron concentrating the fields in this area.
Look at that.
As the pipe heated up, so did the ferrofluid around it, causing the oils to boil off and make a thick white fog. The pipe in this shot was crushed from the current, and when it finally melted through, the sparks ignited the oil vapors and made a huge fireball.
All right, that's the money shot right there. I mean, that's... Yeah, so the ferrofluid aligns with the magnetic field lines. Field strength goes up like crazy. Fluid spikes toward a highest region, and then you have all the thermal heating, the ignition from the arc, so, man, ferrofluid spikes, fireballs, yeah, that's awesome.
I decided to give this another try with a better background, using a piece of wood to offer some contrast against the ferrofluid.
Oh, sure.
All right, here we go.
Establishing a shot.
Woo! That was nice. Let's see what that looked like. Wow, so completely stained that piece of wood black from the ferrofluid, and then it just crumbled that
Magnetic
pipe.
wood.
Nice. I wonder what the current was on that. Oh, it was huge.
170?
Oh yeah, yeah. Yeah, it was 160 at its peak. That was
160.
a really good shot. Well, for the new Switch configuration, holy
Heck. Sadly, I had bumped the camera lens out of focus for this one, which is such a shame because this shot was destined for greatness.
Man.
This was my last bit of ferrofluid too,
Still
so I
looks good.
almost called it quits here and settled on the earlier shot. I realized that if there was one shot to do right, it was this one, so I ordered another bottle of ferrofluid to give it yet another go.
Alright, so I'm gonna go camera, light, yeet switch, and back to the camera. Okay, here we go. Jeez. Wow. Whew. That is always so surprisingly loud. Yes, yes, that was finally it.
I love seeing him happy.
This was the shot right here, and I think it's the coolest thing I've ever filmed in my life. In the span of a tenth of a second, nearly the entirety of the dish of ferrofluid was
Spikes.
slammed up against the pipe, while the total circuit power rose to over 10 million watts. One detail that stands out to
Yeah, 160,000 amps, 60 volt transient. Yeah, that figures out to about 10 megawatts.
me is how the smaller bits of ferrofluid in midair are aligned with the field, and
Love
another
it.
is that many of the particles take a spiraled path inwards. Just like in the other attempts, the pipe implodes from the 160,000 amps that it passes, and once it melts through, it ignites the hot ferrofluid to make a huge fireball.
Again, that high magnetic pressure causing an implosion. Same effect used in Z-pinch plasma compression and fusion. Difference between him and fusion research is scale and containment.
I think it will be hard for me to ever top a shot like this. I've already
Oh, I'm sure
mentioned
you
that this
will.
video was not my idea. It was actually the company AnyDesk that reached out to me and wanted me to experiment with a bunch of car batteries. And of course, they bought me all the batteries as well as the supplies I needed to make this video possible. Now, the fact that a video sponsor came up with the best idea for a video on my channel is still just astonishing to me. I know
for them.
AnyDesk is going for the whole Red Bull of science kind of vibe, and they really hit it out of the park with this one, because this was a genius idea for so many reasons. It's one thing to make an electrical video about something like capacitors or Tesla coils, and although these can be a lot of fun, these aren't things that most people can relate with. But car batteries? Everybody knows what those are, and everybody knows they are powerful. It goes far beyond the clickbait appeal though. These car batteries gave me currents rivaling what's seen in multi-billion-dollar facilities. They allowed me to poke the fundamental
Yep.
forces of the universe, and as a result, they allowed me to take footage unlike anything ever recorded before. You can thank AnyDesk for making all of this possible. So at this point, I've ran out of time to continue the battery experiments. I mean, winter's clearly here, and the cold
Snow
temperatures
on it.
dramatically limit the kind of current I can pull from the batteries. That means that any further experiments will have to wait until next year when it warms back up again. So, what will I do with the batteries until then? Well, they're just gonna hibernate out here in the yard.
That's
Now, I
awesome.
know this is surprising to most, but the rain and snow really aren't bad for them. I mean, the only critical detail for storing them in the cold is that they're kept fully charged. I mean, the first 100 have been sitting out here for 2 years now. Oh my gosh, the snow is blinding me. But those 2-year-old batteries still test almost new, just because I've always kept them fully charged.
Yeah.
Now, if you're curious how I've been charging the batteries, I've just been using this 1500 watt power supply here. Now, if you think this seems small, well, it is. It's just that, every experiment with these batteries takes a lot of prep. So in a typical day, I can really only do a few shots, and, that doesn't really discharge them by all that much. So, slowly charging them with this thing is more than adequate. Now, I will say that it feels like I've barely scratched the surface of what's possible with these batteries. It's just that I spent so much time working on the Switch that I didn't have time to get through all the experiments that I wanted to. So needless to say, there will be more videos with these batteries in the future.
That's awesome.
Now, as far as future experiments go, there's a lot I have in mind. I really wanted to melt tungsten underwater, as well as some other underwater experiments. So that's probably like the lowest hanging fruit of future experiments I can do. Now, I know a lot of people want me to wire all these things in series here, but I really just can't think of that many things I'd do with that kind of arrangement. I mean, yeah, I could draw some just ridiculous arcs, but other than that, I really don't feel that it's worth the effort or risk, really. Now, that being said, I did arrange all of these battery sub-banks, rewire this bank to 500 volts. And, 500 volts at 20,000 amps,
Ooh.
I think there's a lot of fun to be had there.
There is a more interesting way to get higher voltage from.
Yeah, 500 volts. So before that, low voltage, high current, arc hazard, magnetic hazard. At 500 volts, now you're going to add shock hazard in there. Plus sustained arcs are easier and flashover risk goes up. So yeah, you're getting into serious substation hazard area here, even more so when you start to crank up the voltage a bit.
The batteries though. If I were to stick a big coil in the circuit, that would allow me to get these big currents also at a high voltage. So the idea with that is that you'd build up a bunch of magnetic energy in the.
Okay. That's how railguns work, so okay. Maybe that's his next plan. But yeah, that's essentially pulse power design would be to put a big coil in there.
A coil, which you can then release in an instant in this just enormous pulse. So if I wanted to build a railgun with these batteries, that's how.
I feel like I've watched too many of his videos. The fact that we were both aligned on railgun for a sec.
I would power it. And even just for like blowing things up, if you stick a big coil between the batteries and the load, it's going to make the explosions a lot more violent.
I'd like to give a special thank you to Greg Lay.
And as far as keeping the batteries outside, I mean, yeah, there's going to be a bit of corrosion risk, and it's not ideal. I mean, nuclear power plants don't keep batteries outside, even though we keep them charged. But yeah, I think what he was getting at is it's not as high of a risk that a lot of people think they are.
Seth Miller, Bert Hickman, as well as all of the members of my Discord for the advice that they gave me throughout this project. I'd also like to thank all of my Patreon and channel members for all of the support.
This was an epic video. I mean, this entire project demonstrated that magnetic pressure scales with current squared, basically validating all of Maxwell's equations. Plasma formation is going to dominate high current events. And yeah, you're going to, even little bits of instabilities go a long way. But what impressed me the most was the fusion adjacent instability realization. And he independently stumbled into the same physics that limits tokamak stability and governs Z-pinch plasma physics in confinement. That's really cool. I mean, after all, he's in pre-fusion current regime. That's a thing. Still about an order of magnitude or two short. But the main difference between him and a billion-dollar facility is containment, control, repetition, and measurement. I mean, after all, Maxwell's equations don't care if their funding is a national lab or a YouTube sponsor. Thanks so much for watching. I'll see you next time.